So you want to build a guitar pedal? Well, then you've come to the right place, because this is episode 1 of a 10-part course on how to build a digital guitar pedal completely from scratch. This is not just some course where I will teach you how to make exactly the pedal that I'm going to make, but instead I'm going to teach you all the skills and knowledge you need to take your own custom idea from start to finish. Throughout the course, I will be making this chorus pedal that you can see right here. But again, you could come out the other end with a pedal that is twice as big with 5 times more knobs and your own custom graphic on it. In the course, I'm not just going to show you how to physically build the pedal, but I'm going to show you how to code for the DaisySP, which is the microcontroller we're going to be using. I'm going to show you how to make a custom drill layout so that you could have 10 knobs, 2 LEDs, 5 foot switches, and whatever custom layout you want. And then I'm going to show you how to make a custom PCB and KeyCAD and source parts and look at the data sheet to make your own footprints for KeyCAD. And then I'm going to show you how to make sure that the PCB will actually fit with the enclosure and the specifications for the drill tool you made. And then I'm going to show you how to make a custom graphic in Adobe Illustrator that we can get UV printed on top of the enclosure, which we've ordered the drill schematic for, so we don't have to touch a single tool. And then I'm going to show you how to assemble everything, solder it together, and then have your own custom pedal by the end of it. All right, that's a lot. So who is this for exactly? What are the prerequisites and tools you should have before you start this course? Well, nothing really. I mean, I made this course for beginners. This is not some intermediate advanced course, even though a lot of the topics covered kind of tiptoe into that territory. But I wrote it so that you could have little to no knowledge and hopefully come out the other end with a pedal. That being said, there are definitely certain walls that you will hit if you have literally no knowledge going into there, so I do intend to have moments where you might need to pause the course and go and learn something and then come back. I would say this course is best for somebody who has just a little bit of knowledge in each category. So maybe you've programmed a little bit, or you know some basic components and you understand what like a PCB is or something. But it isn't exactly a fast moving course. So if you don't know what any of that is, I will still at least tell you what you should look for if you have those gaps. Also, in every description, you will find a GitHub that is linked. This is the course's GitHub repository. In there, you will get all the code that I write throughout the course. You also get the KeyCAD files that I use and my Adobe Illustrator files. So if you'd like to just make the pedal I make to get started, you can totally do that. I've also included a lot of extra resources that I mentioned going along in the course, like all the parts lists that I buy from Tata Electronics and some learning resources that I've used in my own journey and some recommendations for you. This course is also sponsored by PCBWay, a quick, cheap, and well-made solution for getting PCBs custom manufactured. I'll show you how to order through them later in the course, so stay tuned for that. Without further introduction, here's the first section of the course where I will just teach you all about the DaisySP and how we can go about hooking up some basic components. Enjoy. Welcome to section 1. This is going to be the coding section. I'm going to keep all these sections kind of unscripted, sort of just talk and teach and get airs and go on tangents and things without keeping it too long. But yeah, you can always watch it on 2x speed if it's too slow for you. But to start off, I just want to go over the DaisySP. This is the tool that we're going to be using to put our code onto within the pedal that'll be generating all the sounds and kind of just the hub for the entire pedal. If you know something like the Arduino, that's kind of what this is, except this is dedicated for audio. You can technically do audio stuff on the Arduino, but it won't be as high quality and there'll be just more hoops to jump through. Whereas the Daisy is just this like very nice one-stop shop, high fidelity. And they got great kind of code that you can sort of use this library that we'll see in a sec. This $21 is for this low memory version, but if you want the soldered pins with the full memory, then it'll cost you about $30. And you can go and get it unsoldered and these pins will just come separately, which I typically do because it doesn't really take much time. And the 1 megabyte versus 65 megabytes, this is something they did recently, which is really cool. You can kind of just see here what the sort of applications it would be for. I haven't tried the exact code that we're running today on the 1 megabyte, but for guitar pedals and the amount that you probably want to add, I would just go with the 65. As you see here, this is for like non-bass time effects utility stuff. I had made a couple pedals with that before and it was fine. But so why would you want to use the Daisy? Well, as I said, I mean, you can just put C++ or Arduino, Max, Pure Data right on there. So if you know any of those things, even a little bit, I mean, programming, you don't like really need to know huge C++ or anything, but if you've kind of programmed a bit or done any sort of the visual programming languages, this will translate very, very nicely for you to get to just have examples super quick. In terms of why you would want digital over analog, in my opinion, a lot of it is on versatility and sort of the entry point to create unique stuff. Like you can go online and buy all these little kits to make certain pedals, analog pedals and everything, and those are really nice. But if you were trying to design your own complete unique device from scratch as an analog circuit, you're going to need a lot of experience to be creating things like big delays or these intricate reverbs, pitch shifters, all these things. Even if those will have digital components, which I'll show you in a sec, it still is a lot more to learn, honestly. I mean, electrical engineering is pretty complex, and we'll do some of that in this course, but the bulk of it will be programming, which is also very hard and dense. But you'll see, especially with the Daisy, they have this library that has all these kind of little modules already pre-written that we can do as great starting points. So I think the entry point to the Daisy Seed is incredibly small and good for anybody that loosely has kind of used computers and programmed and stuff. If you haven't too, there's still, like I said, it's not like this super dense programming from the start. It can be that if you want it to be, but it also can stay like this in the same way as you could make some analog little distortion pedal or something, and it can be relatively simple. But I wouldn't say it's simple to truly understand what every single electrical component is doing, and probably if you've just made some kits, you don't actually know that, which is fine. And in this code, you might not totally understand it, but yeah, there's other digital solutions. There are these kind of old little devices that are really cool, honestly, but these aren't necessarily in competition with the Daisy. This is this old, here, let me find a data sheet here that'll say what effects it has. So this one, you can get a chorus, reverb, flanger, tremolo, pitch shifter, pitch echo, and then reverb. And what this is, I don't know when this came out, a very long time ago. This was used in a lot of those like Eventide pedals that you see and stuff. And this would be like if you had this pedal that's probably mostly analog, but you wanted a pitch shifter or maybe the reverb they have, because these are just like completely baked into the chip, and you use these kind of, I think there's this kind of visual software that you can use to sort of program it, which it looks, it's a bit outdated. There's still pedals that use it, but again, like you can only use these. But yeah, you'll see this in a lot of pedals. If you go on stuff like Pedal PCB, I'm sure that some use these sort of digital chips. But again, that's not really competing with the Daisy. They kind of serve different purposes because those are just locked in. But they will give that kind of fun, like vintage digital sound because they're really specific and you might actually recognize some of it from pedals that you had used in the past. But yeah, so the Daisy gets you pedals like this. This was one that actually came out quite recently from Glitch Cloud Audio. And I checked into their specifications and stuff, and it was Daisy Seed. I don't know like how, like that doesn't always mean that 100% of it is just like this Daisy Seed in there. But yeah, you see a lot of these kind of modern digital pedals that they're like super feature rich. That's a very like Daisy Seed thing. This company is also by the guy that does that started the Daisy Seed. I think he started this beforehand, Andrew Eikenberry. This is, I don't know if 100% of their stuff is, but they heavily obviously use the Daisy Seed because it's their product too. And you'll find if you start looking in the Daisy Seed, a lot of it, people are doing modular synth stuff. That's like one of the kind of prime things people are doing it for. Here's this other great company, the Synth UX Academy. They have their own synths, but a lot of their stuff is really cool because the point of it is for prototyping the Daisy, not necessarily like a guitar pedal or a modular component or anything, but they do that, like the Audrey 2, which is a really cool device they have. I have a few over here that I'll show you in a second, but they have something like the Simple Fix kit I'll show you is like a really good kit if you're trying to just prototype on the Daisy and you don't want to go out and buy a ton of parts that you might not have yet, and you can just hook that up and use it. Daisy Seed. Here is everything I have made that I kept for myself with the Daisy. Mostly guitar pedals, as you can see in the middle here. And then this is the stuff from the Synth UX Academy that I had mentioned. This is this kind of big synth template sort of thing. This is this touchpad. This is that little prototyping board. You can also get the Daisy Pod, which is Electrosmith's own little prototype board. I think this runs for around like $70. This one's for like 100. These are a little bit more, but yeah, these are all great starting points for if you just don't really want to mess with hooking up a breadboard and everything in the beginning, but we'll kind of go over that stuff later. These two pedals are made with the Terrarium PCB, which is this sort of PCB that you can get on pedal PCB. I did make a video on this many years ago when I was first kind of learning about it, and I really like this Terrarium PCB because it's so many knobs, so many switches. And yeah, you can check that video out. A lot of the stuff I'll say here is covered in that, but it's just a little more updated, and we're going to be making our own thing instead of Terrarium. But if you're just kind of interested in getting a pedal that you can code on, then that's a great point to do. I have two of those here. This right here is the pedal that I'm going to be making in this course. So like I said, the point of this course isn't for you to make this pedal, but just a pedal of your own design. But I needed a design to do for the course, so that's what I chose, just a 3-knob chorus pedal. And then here is this glove I made. Again, of course, Daisy seed on the inside, little 3D printed box. And then this really janky wires coming out to a gyroscope that is under the glove, or like kind of inside of it. And then these 3 buttons on the other end. I might make a Bluetooth one in the future and make a video on that, so subscribe for that. And then this right here is a nice prototype board, kind of like these two, except it gives me all this breadboard space if I want to hook up something like the gyroscope or a little LED screen or something, and it has some more knobs and everything. So this is probably what I'll use for this course. I will put this 3D print in the description, the file, if you want to use it yourself. But yeah, these little boxes are really handy when you're just trying to prototype and everything. So yeah, so that's some of the stuff that you can do with the Daisy. It really is super, super versatile, and hopefully your mind is thinking of all these different things that you can make. But for now, in this video, we are going to make a guitar pedal. Before we begin, obviously you will need a Daisy seed. So if you don't have one, you might just want to go purchase one and come right back. In addition to just the Daisy, you will need some jacks and knobs and stuff to get programming with it. If you have like literally nothing and you're starting from zero, that might be a good reason to get the Daisy Pod that I had showed you. This is a great way to again, just kind of get to prototyping right away. And then once it gets to the other parts of the course, you can kind of return to that once you're more confident, or the Synth UX Academy stuff. But another option is if you're just like, nope, I want to do this whole thing, then you can go and buy actual knobs on an electronics website. This is the one that we're going to be using in the course, Tata Electronics, because they sell pedal enclosures with drill schematics, and you can do UV printing on it. So that's what we'll be using. But you can go here and just search mono jack, because the pedal is going to be in mono. And then you'll see all of these jacks here. I think this is the ones that I have on my prototype board. You can also get ones that hook up to PCBs. They might be able to fit in breadboards. I'm not totally sure. But something like this, if you want to get, and then you can solder on to the pins there, and then on the other end have wires to stick in. I'll show you how to wire up everything. You don't have to learn that if you're unfamiliar. But yeah, in terms of knobs, you could also go the Amazon route if you want to get a big pack. These aren't the types of ones that we're going to be using in the pedal itself. I always do right angle potentiometers for the pedals for space. But this can be good for prototyping, and it comes with caps and everything, so that could also be a place to start for you. All right, done with that. Now I'm gonna assume you have a Daisy and some way to play it. Not hooked up yet, we don't have to worry about that. I can show you how to do that if you're unfamiliar. But yeah, maybe you have a pod or just some jacks or something. But we're just gonna get to flashing some code on it. So you can come here and go to documentation. Daisy luckily pretty recently had redone all of their documentation, so it looks really phenomenal. They have the hardware section, software section, so this is such a good resource. You can just look around and kind of get acquainted with everything. But for now, I'm going to go to software. In this course, we are going to be using C++ to code the Daisy. Like I mentioned earlier, yeah, you can do Max, you can do Arduino, Pure Data, which there's this nice kind of modern version, plug data, that can fully integrate right to the Daisy. Rust, there's just all these ways, and like they say, if you are comfortable with C++, they recommend you start there. And even if you're not comfortable with any of these, I would honestly say C++ is the easiest place to start, more because the workflow of actually getting the code on the Daisy It's kind of the most streamlined. It just works really nicely. So yeah, we're going to start here. I'm not going to just fully go over this because as you can see, there's a wonderful guide here and a great video. So I'm going to put links for everything. There'll be a whole documentation on this entire course that you can kind of start, but you just follow this. It's actually very simple. You just install this tool chain. You get the Daisy examples library, which is just on GitHub, and you can clone that. You need VS Code if you don't have it. And now, yeah, we're going to get to flashing, but I'm assuming you've done this now and got that working. They do have some troubleshooting sections if you're having troubles. And I'm also not going to be using in this course the debug probe. I do have one and I definitely recommend you get one, but just since I'm going to assume you didn't get one, then I'm not going to be using mine. So here's my Daisy all set up. This is the breadboard I was talking about if you're not familiar. They're these little prototyping boards, so you don't need to actually solder together electrical components. So if you didn't end up getting one of those little boards, then this is exactly what you want. So I can just stick in these headers right into the board and we can hook up knobs and everything straight to it. But yeah, by now you might have learned, but to reset the Daisy, just press the boot button, which is to the right of the micro USB, press reset and then let go of boot, and that'll just reset your Daisy so it's ready to be programmed or take any code off of it if there was any on it. So now I have this hooked up to my computer and we can go and set up our first project. So my Daisy examples is right here in my documents. This is the repository that you hopefully have cloned onto here. As you can see here, there's a nice helper on how to make your new script. So here I'm just going to type Python 3, and then I'm looking at this line right here. So we do helper.py create, and then I store everything in my projects just like they say here. You might not have my projects from the start, but you could just type my projects / new first pedal, and then we do -- board, and then we are on the seed. Right here, this is meaning like if you have the pod or they have the pedal and stuff, or the patch, then they have some specific helpers for that, but we're on the seed, so yeah. And then over here, you see it actually created my project because mine was normally plural, but that works out. Here is my project. And now we want to come over in VS Code, and don't just open up this C++ file. Like it says in here, you actually have to open up the entire folder so that it has all of its dependencies and things. Let's go to Daisy examples, my project, and then hit open. And now hopefully you will see all of your code and it won't be full of errors. If there is errors, then you might just want to go back through this, make sure that all of your dependencies and paths and everything are set correctly, which I think they have some pretty good troubleshooting listed here if you're having issues. Another thing I like to do that they recommended there just before you really get to start working is you can flash some of their examples on, like the blink example. So if we just want to open the blink, I'm going to go back to Daisy examples. If you go to seed here, these are all these examples, and then within DSP are ones that are kind of more like the stuff we're going to be doing for the pedal, but I can go to blink here. And then as you can see, to flash code on, we want to go to run task and then hit the build and program DFU. And this is important to know if you're just starting off. This error 74 will always appear. That's a good sign. That means you're fine. So don't worry about it. So as you can see, our LED is blinking. Not, the coolest, but it just kind of confirms that your Daisy is all set up and ready to go. So it's a great place to start. I'm just going to reset that though. So back to the new project that we created. You'll see this has a slightly different template that is not the blinking. And what this actually is just feeding the input into the output. So this will just completely monitor what you're playing. But as you can see with my current Daisy, and maybe yours, there's no actual jacks or anything hooked up at the moment. So we have to do that. How we do that with the Daisy is we need to see the pinout sheet. So you can literally just go and search DaisySP pinout. Click this. I think this is just where you go and buy it. It has a nice pinout. I honestly click this a lot. And then we can see all these numbers with all these different things on it. This is just showing basically where we need to hook up things, like where we'd want to plug in our knob, where we want to plug in the jacks, where we'd want to plug in a power jack or anything. So it says things like, you can see these out, audio out 2, audio out 1, in 2, in 1. So that would be if you want stereo audio, you can see there's 2 ins and outs. We're just going to be using 1 for this, but yeah, and it actually shows it here kind of in terms of programming. So you can see, it seems I can't zoom in, whatever. In 0 and then size. So 0 is going to be this in 1 channel, and then 1 will be our in 2 channel. And then there's all these ADC things listed here, and then D things. So ADC will be for things like knobs, because those have these long analog ranges that they send. And then the digital will be for things like foot switches, LEDs, and everything that are just kind of on and off. So before we get started, one of the first things we'll want to do is to actually hook up the digital ground and analog ground. If you don't know how breadboards work, the plus and the minus are all connected in rows, or not, they're not connected with each other, but the minus is all connected in one row, plus is connected in a row, and then everything else is connected in these columns. So these, 5 are connected, and then everything there is connected. So with the Daisy, you can see on this end, we have 2 little spots that we can put it in the bottom, and then at the top we have 3 options. As you can see, I've also connected the 2 grounds of this one end of the breadboard so that I could connect one ground here and it'll just auto be connected over there. So I'm gonna take 2 little wires from a little kit I have that I recommend you definitely get. But if you go on your pinout, you can see the bottom left and the top right are our 2 grounds, so we can just hook those up. And now that should be all good. So first I'm just going to show you how to technically hook up the jacks with a way that in no way do I recommend. But if you're really wanting to get going and you don't have one of the kits or a soldering iron or anything, then this does work, but I expect it to be very noisy. So here I got these things called alligator clips, which you can squeeze and they will open up, and therefore just connecting parts. Basically, you can just squeeze them on pins or components and they will conduct through them. So if I just take our jack here, and you obviously will need 2 for the in and the out, I can connect one like this. So this is with our actual audio pin, and then I need to somehow connect it to there. So I'm also going to get these little jumper cables, but any kind of cable will work. I'm going to connect it to the one end, and then we want to go 5 down, 1, 2, 3, 4, 5, to be in audio in 1. So then I want to do the same thing with the ground pin, and then we can just put it anywhere on the blue row right there. Now I'm just going to do the exact same thing with another jack right here. And then this time I want to go to the audio out 1. You definitely want to make sure you kind of pick the same ones. It would be annoying to have audio out 2 but in 1. Okay, so here's this really janky setup. This is our input, this is our output. All right, as you can see, I have my pocket operator here. I'm going to plug everything in, and as I expected, it is quite noisy. Let's see if we can hear anything. Yes. But now we're ready to hook up our first potentiometer. I'm not going to show you it as in depth as I just did because it's the same concept of what we just did with the jack. But this time, instead of hooking up to the audio ins and outs, we are going to be hooking up to one of these ADCs here in yellow. It genuinely does not matter at all which one you pick, as long as it's one of these 22 to 32 pins or the 35 right here. What a potentiometer is a resistor technically, in which when you turn it, it is changing the value of the resistor. But for us, the Daisy is going to convert all of that into numbers, and we can just easily normalize it from 0 to 1 for when you are left and right completely. Potentiometers, or pots for short, have 3 different legs. The left one is ground, the middle one is called the wiper, and the right one is your power or voltage. The wiper is what we're going to plug into that ADC. On the pinout, the ground pin will go to ground, and the voltage pin will go to this 3v3 analog. So you can pretty much hook the wiper up to any one of these. Like I said, you just need to note what the value is in reference to the pinout. You don't need to know this actual pin number here. You just need to know the ADC 012 or whatever. And then yeah, you'll need to hook it up to the analog ground and digital ground that we had already connected on the breadboard. And then you'll need an extra thing coming out of this 3v3 analog to connect to the right pin. If you have more knobs, feel free to connect however much you want. To start, I'm just going to be using one for a little bit. And eventually I'll have 3 in my pedal, but you can have as little or as many as you'd like in yours. But I will be showing you how to configure for multiple inputs within the code. All right, so here we are back in the code. I'm just going to kind of explain what all of this is and how the Daisy code is kind of set up and works. I'm going to assume you have some general knowledge, like you know what a variable is and maybe a for loop or if statements. I'll kind of still go over stuff loosely so you don't have to be super knowledgeable, but I assume that you've watched some videos and are at least somewhat acquainted with any programming language. Maybe you've touched something like Python or does some like web development or something in JavaScript. So I'll kind of explain some of the more C++ things that are specific to here, but there's honestly not much at all, at least for what we'll be doing for this. You can see here we have like your include. So this is just including the Daisy seed and some helpful things they have for that. And then the DaisySP library, which is that library I mentioned that's just full of all these helpful DSP things and that we'll definitely be touching later to do our chorus effect. This using namespace is nice. It just kind of shortens how much we have to type. So it's a good thing to say. And then I'm also going to do using namespace Daisy seed. Oops. Since we're going to be using the Daisy seed. So there's just a few things there that'll be nice to have that written out for. And then this is where we actually declare the Daisy. This hardware variable is going to be, as you see, where we like initialize and do all that. So starting off, here's the audio callback function. This is just where all of the processing is done. I'll explain more about kind of digital audio in a second, how that works. But then here is your main function, which just runs right when you boot up, the Daisy. So that's why we have like initializing and setting sample rate and everything is in here. But yeah, the audio callback here, you can see we have our inputs and output buffers, which will hold, they're basically arrays of all of the incoming and then the outgoing numbers, and then we have size here. This is a for loop, which is looping over all of the incoming data from whatever we plug in, and then we can take those samples and do stuff to them. So I feel like we do need some sort of understanding of digital audio and what exactly is coming in to us and what our data is. So you can see here, this is how our block size is set. It defaults to 4, and this is the number of samples that will be handled in our callback. If I assume you've used DAWs and stuff, so that's like your buffer size, which you might be thinking, like in a DAW, you are typically like 256, 512. Sometimes you're going all the way up to 5,000 and something. But in a DAW, we'll obviously be running so many more effects and also just your computer's running your whole operating system and everything. So buffer size like 4 would be way too intensive, whereas the Daisy is just running this simple code here. So 4 is totally fine. If you are finding that your pedal is glitching around or something, then that is a value you could play around with. But that just basically is saying how big these buffers are going to be in this audio callback. But it's not something you really have to worry about, because as you see here, the first thing that they do is give you a for loop, which is just a way to loop through something, typically like an array or a list or whatever, which is what the buffer is. So it's just looping through it, making sure it's the size, which the audio callback handles, and that's going to be 4, but it's just said right there. And then we can just apply all of our processing to each individual sample. But you can always just kind of think about it in these single little numbers instead of like the overall signal. Even when we deal with delays and everything, those are still just kind of referring to the current one and then maybe the one before it or something. So you can really kind of just ignore the for loop and now just be inside of it and do all your processing there. To just understand what this is saying, your output buffer, if that's just a variable that if you set it, it's going to be how your output sounds like. So here you can just say it's saying the output at channel 0, which this corresponds to that pinout chart. So if I bring this back, you can see out 0. So that's just if you're plugged in there, that's going to send to there. If that said out 1, which the right below it does, and that's going to be the other one. This just does both. I am only hooked into 0, so I can just delete this if I wanted to. I is just saying which sample within that input buffer we are going, or the output in this case, that we want to change, and then that will be mirrored in input, which is also that same channel, and then which sample it is. So that'll probably be a number between 0 and 3 since our block size is 4, but that doesn't really matter. We just can say I, because then we could change this to 128 or whatever, and it'll still function exactly the same. So the first thing I want to do is just code a really simple distortion, just a hard clipping digital distortion. That's probably not going to sound great, but it doesn't really matter because I think it's a great kind of way to just get your head understanding how DSP works before you start doing more time-based effects, which are definitely much more complex. So dealing with delays, reverbs, filters, and everything. With DaisySP, we won't really have to worry about that, but I think since DaisySP, we'll just kind of be able to simply throw a chorus on. I think coding a distortion from scratch is both very simple and then nice to not have to rely on another thing. So to do a distortion, I mean, you can think of a distortion in your DAW or other guitar pedals you have and how that works. You might be familiar with the terms hard clipping and soft clipping. I'm not going to get into it that much, but hard clipping is just once you're above this certain threshold, just hard cut and say, no, we want it to be back down to here, whereas soft clipping has more smoothing. It's kind of in digital world used to replicate old analog stuff that will naturally have soft clipping because hard clipping can't really be a thing in the analog world. But we're going to do hard clipping because it's simple to program. And how that works is essentially you just take your audio, you amplify it a ton, and then you hard clip and you say, go back to a normal range. And then that just distorts it. It clips, like in your DAW when you just are going above, and then you limit it, and now it's still distorted, but you're not blowing your ears out. So you can think of our input signal coming into the pedal, into our input buffer. It's a very complex signal, obviously, but just think of it as like a sine wave. In the Daisy here and most kind of software digital things, when you're coding, the range will be from -1 to 1. And in our sine wave, according to the sample rate and everything, there'll be all these discrete points along it that we're sampling at. And those are just numbers. Those are just numbers being fed into this buffer that we can mangle. Like we said, a distortion, all we are doing is amplifying. So if all those numbers are just showing amplitude, then to amplify it, we just need to multiply them by a certain number, let's say 10. So we're multiplying now every single sample by 10, and then we want to hard clip it. So we do that by saying just if this sample is above 1, which was like our base range, or below -1, just put it back to 1 or -1. And that's literally it in terms of a simple distortion. It's not going to sound great, but then we can determine the amount of distortion that we'd like by that gain thing so that we can map that to a knob. So coming back into the code, if you've coded before, I hope that this is something that you could maybe try and do on your own and figure that out. If not, it might still be a little bit daunting, and that's totally fine. But yeah, first let's just declare our distortion variable. So I can say float distortion amount, and let's just set it to 0. So then down here, since this is just simply putting input into output, if we want to do all this processing, we don't want to just be throwing it into output every single time. So instead we can create a new variable that's just locally in the callback function. Let's just call it wet signal or maybe distorted signal. For now, and then here I can say distorted signal equals, and then like we said, all we want to do is amplify it or multiply it, so I can just take that times distortion amount. And actually the default here we should actually put to 1, because obviously if we times it by 0, it'll be completely silent. So default, we'll just set it to 1. Distortion amount. So in pseudocode, as I explained earlier, we say if it's above 1 or if it's below -1, then set it to 1 or set it to -1. And luckily, that's not really even pseudocode. That's pretty much just exactly how we code it. So I'm just going to say if distorted signal is greater than 1, then distorted signal equals 1. And then we could say else if distorted signal is less than -1, distorted signal equals -1. And that's it. Then we just have to go and take our distorted signal and feed that into the output. So I'll take out, get our channel, which is 0, get which index we're at, which is I, and then say equals distorted signal. So before I flash this on, first off, we need an actual distortion amount. But I also just want to say, when you're dealing with audio like this, really be careful when you go to listen back and play stuff, because say I put this to 100 and then maybe I did not write this, or I commented it out accidentally or something, or forgot to uncomment it, then that signal is going to be 100 times louder, which could destroy your speakers or destroy your ears, more importantly. So always in a second when we'll turn this on, make sure your gain starts down on your interface, or your headphones are down, or you play it in speakers ideally when you first start. I trust that this will work because that's exactly what the code does, but never trust it. Don't be too overconfident, because then that's when you mess stuff up. So for now, I'm just going to set distortion amount to like 10 probably is fine, and then flash this code on. So make sure you reset boot and then put it on. All right, I did end up switching to my Daisy pod just because the headers on this were being really annoying in the breadboard, because they got to be filed down or something. They're really thick, so they kept popping out. But I got the pod here, and let's hear this distortion. So if I just turn this up, it's probably gonna get really loud. But we got distortion. Probably sound a lot better on a guitar, but I just have so much set up here that it'd be really annoying for me to do. But I do just want to show you how even just this simple hard clipping distortion and the knowledge we gained can be easily then put onto other things. Like if I were to search DSP soft clipping equation, and then I'll do the first one here. Like you could see this, and to some people, I mean, if you haven't like done math in a while, it might be kind of complicated, but when you really read this, it's saying when x is less than or equal to -1, make it -2/3. When x is in between -1 and 1, make it x minus x cubed divided by 3. And then when x is greater than or equal to 1, make it 2/3. And I mean, that's nearly code language. So we can say when x is greater than, and then this says or equal to, then we do 2/3, right? So I can just you could actually write that out, or you could write 0.66, it doesn't really matter. And then when it is less than or equal to, we want to set it to 2/3. And then I can just say else, because if it is not between those, then we know it is going to be in the middle. And then remember, x in this case is just this distorted signal, because x is your input, and right before this we set our input to this. I could just say distorted signal equals distorted signal minus, and then I could do parentheses here. We just want to cube the distorted signal, so I could literally just write out distorted signal times distorted signal times distorted signal. And then we want to take all of that, so we have to put it in parentheses, and then we can divide that by 3. I did forget a negative here, so make sure to put that. And I would change your distortion amount down a bit. This is something you can play with, especially if you have a guitar lying around. Soft clipping would be good for not as much distortion as I was just throwing into the hard clipping, so yeah. Hard to hear the difference with the drums I have, but maybe you can if you're playing around with it. But yeah, this is a great way to just kind of get really familiar with how DSP works and things, is simple distortions. I think they're a great beginner point. You can see like here's somebody, I don't know if they're asking for help, but yeah, like here's another thing that you can implement, and it's just a ton of if statements. And they're kind of doing this differently. Instead of applying a ton of gain, they're putting the threshold in which they start compressing. That's what you change. So it's interesting. You can kind of just play around with that. Okay, but staying with this code, or the hard clipping one, it doesn't, I mean, do which one you want. Obviously distortion amount, great, but we would want to control that, right? So we should use that knob that you might have hooked up earlier. So to get that actual signal from the knob, on the Daisy documentation, they have this section here in tutorials. If you hit ADC inputs, this is a really great resource for this. It's pretty much exactly what I'm about to teach you. So if you want to learn more, you can kind of read through this whole thing. But yeah, we essentially are going to be declaring this ADC channel config. But before we do that, it's a great thing to just get our kind of the pins that we have connected all of our knobs to, and actually just fully define them. So in C++, you can do this define keyword here at the top using a hash symbol, and then we can just say define pot1, and then whatever that ADC pinout value that it was, you just write A and then whatever number it was. So you don't have to write DC or anything, but if you hooked it up to ADC0, you just type A0. This will throw an error if you didn't do this DaisySP namespace, so definitely do that. For me, like I said, I'm using the pod, and while they do have, when you declare your new project, you could say that the board is for the pod, and there's some really great kind of easier ways to declare the knobs. But since we're going to be making our own pedal in the future, I'm just going to treat it as if we're on the seed. So I'm going to the actual pinout here and seeing which ones they have it hooked it up to, which it seems that pot 1 and 2 are A6 and A0. So I'm going to just declare that. So just write every single pot that you ended up hooking up. I'm going to do pot 1. I think this one they called A0, and then this was A6, and you can just do the same. So now if you only have one knob hooked up, there is a, using the ADC channel config, it's really easy to just initialize a single one, but I'm going to treat it as if you have multiple, as I do, and since we will in the future, you actually don't need semicolons here. But yeah, so as you can see here, they have this really nice kind of tip of naming your ADC channels using an enumerator, which is just a C++ thing or many coding languages that we can write out all of our knobs, and those will all just technically be integers behind the scenes. So I could say enum ADC channel, and then depending on how many knobs you have, this is where you'll write them out. So I have just 2 on the pod here, so I'm going to write knob 1, knob 2, and then for the last value that you put, you can just write number of ADC channels, because that'll be the number, since this is 0 index, so knob 1 is technically 0 behind the scenes, and this is 1, then this will be 2, which is the exact number that you have before then. And make sure to put a semicolon at the end of that. So I'm just going to make our own function down here just to keep things tidy for initializing all of our analog to digital stuff. So I'm just going to say initialize ADC, and now we can initialize everything. So I can just say ADC channel config, and then ADC channel config num of ADC channels. So now we're just declaring an ADC channel config array that is the size of the amount of channels we had, which is why that enum is so helpful. So now we can declare all of our knobs by saying ADC channel config, and then we can use our enumerator to get the index of which one we're initializing. So I can say knob 1, init single, and then pot 1, and that's all. So then you can just go through and do that for every single one that you added. So I'm going to say knob 2, init single, pot 2. And then we have to actually tell the Daisy to initialize this. So we just do that hardware variable up here, .adc.init, and then we can feed into that the ADC channel config. And I think we have to give it the number of channels, so that we can just give again that enum right there, number of channels. So perfect. Now we can just put that in the main function. So now that will all be initialized. And then we can make another function for actually processing all of that and putting it into our variables. So this is also really easy. We just take this distortion amount that I'm going to put with knob 1. So I just say distortion amount equals, and then we do that hw.adc.getFloat. GetFloat is your normalized. So this will be from 0 to 1, 0 when it's all the way on the left, 1 when it's on the right. Get will give the like raw potentiometer values, which I think will go up to like 65,000 or something, or 6,000, I forget. So I don't really know why you'd want that. You can always multiply this by whatever range you want, which we're going to do. But I just say get float, and then I'm just going to set knob 1, but then this is where you can just easily pick which knob you would like. So yeah, this is again the define up here. That's just going to be used for initializing this, but then from now on you should use this enum here, because you're telling it which channel of our config you actually want to grab that data from. And now there's a couple things we can do here. Later with the chorus, I'm going to show you this nice fmap function that comes with the DaisySP library, but you can also just do some math. So in this case, we want, say I want it to go up to like 50, then I can times that by 50. But you have to remember that the lowest value of this is 0, and if this were being times by 0, it would obviously be silent. So then we also just want to hit +1, and it's that simple. So this will technically go to 51. So this will go from 1 to 51. Okay, one thing, yeah, I totally forgot to do is these functions are declared after I'm actually calling them. So in C++, I actually have to throw those. Let's just put them here, and I have to say void. And so now it'll actually know that function. And then while we're doing that, I also totally forgot to even put the process ADC. So let's declare that up here. And then we have to actually put that in our audio callback. Not the main, because like I said, this is just runs once when you initialize the Daisy or when you like plug it in. Whereas up here, this is called very, very often. So we do all of our processing in here. I also forgot that you're supposed to do the hw.adc.start after you do a init. So make sure you have that. And now we're ready to flash the Daisy. So now we have a distortion with an actual controllable distortion amount. Later we'll get into how you can do nonlinear mappings, because obviously right now this is just pure 0 to 1, and you might not need those super high ranges until you're at the very end. So we'll do that in a sec. Now we can finally move on from this distortion and get to coding some stuff with the DaisySP library. Like I mentioned before, DaisySP library is this amazing DSP library by Electrosmith. So it's made perfectly for the Daisy, and it just has a ton of different effects, processors, all these things. Here I am just on the GitHub page for it. They do have stuff listed. Here they have all these references and everything, but I don't think it has anything as nicely written out as this. So here you can see all of their different things: control signal generated, drum synthesis, all this stuff. Effects processors is kind of the guitar pedal stuff, or for us is guitar pedal stuff, but there's so much for modular synths and just nice like utility classes and things. But here you can see like auto wah chorus, which we'll use, decimator flanger, overdrive, so much pitch shifter, some very cool stuff, and it's super easy to implement. And once you learn how to do one, it pretty much applies to everything. So basically to kind of figure out how what functions and methods are available in these, I think here might be a nice place to do it. So like if I search chorus, I was right there, I can click chorus here, and then it will just tell me all of the different methods for this class that we can implement. So you can see pretty much every single one of all these processing ones will have your init, which we will put in the main function. You have process, which will be where we actually give the input, as you can see here in that the process block, and then all of the parameters, which is in the process ADC, where we would put that. And then if you're on the GitHub, you can also just click the header file, the .h file, which in C++, that's just where you put all those declarations, so we don't run into the stuff that happened to us earlier. But this will also just kind of have everything nicely laid out that you can see, but it's a little better over here. So if you want to put a chorus, which again, I'm doing a chorus, but you could pick anything from that list and do that if you want. I am going to delete all of this though first. So here I can just say like sig or wet. There's a lot of different, do whatever you want, but just something else. But distorted signal, I'm going to delete distortion amount. So we need to declare some variables. First, we can just declare our chorus just like that. It's literally whatever name will be listed up here. You can see it says to say this include chorus H. By default, you'll have the include DaisySP library, so that will literally just include everything. You could, I guess, take that away and just write chorus, but might as well just keep the whole thing. So I can say chorus, and then we can kind of declare all the different variables we want for it. So I was going to do just 3 knobs because that's kind of simple, easy. A lot of choruses only have 3, so you can kind of pick which parameters you would most want, and then others you can just have like preset for whatever type of sound you sort of like. So here I'll just write a feedback, which even if this is something you're not going to have a knob attached, it's still good to declare. So I'll do that. I'm going to do delay, milliseconds. It's nice to kind of write that out. And then rate, which I think I'll have rate depth, and yeah, those will be the changeable ones. I'll just default them to 0. And I'm also just going to throw a filter too and do like a little tone knob just so we can get another DaisySP thing in there. So if I go to filters, we can see the different ones. A one pole filter is just your standard low pass or high pass filter, and that's all I want is just a low pass filter. So as you can see, it's just called one pole, and then it's the same init process, and then as you would expect, a set frequency and then set mode, whether it's high pass or low pass. So up here, I'll just add a one pole and call it LPF for low pass filter. And then I will add a cutoff. Okay, so there is all of my parameters. So the next thing we want to do is to actually initialize these. You could make another function for this, but I'm just gonna write it here. So we got our chorus initialize, and almost always you're just going to be feeding in your sample rate for this. So I'm just going to declare a little sample rate variable here, and then you can just do hw.audio sample rate, and I think that'll just return a float. So we can just nicely pass that into, oh, not there, to our chorus and our low pass filter, which does not seem to actually take anything. So that is good there. Now I'm just going to set the few things that I know I'm not going to be automating. So I was going to do set feedback, delay, and then I'll do the low pass filter. I'll set the filter mode. And then here it's telling us how to get that filter mode. So I could just go one pole. See here, this is why we do the namespaces, is because since we're using namespace, we don't have to write DaisySP : we can just do one pole, filter mode, and then I want filter mode low pass. And then I can set the initial frequency, I suppose, to cutoff, which I'll put up here as just like 10,000. So that is all of those. Another thing that I really like to do that I'm actually going to put in here is there's that little LED on the Daisy. There's one that's always on when you plug in, but there is another one that you can actually program. That's like that code where it blinks. I find it really helpful just whenever you plug it, put your code on for that light to light up. And later we can map it to like the bypass or something instead of hooking up an LED yet. We can just do hw.setLED true. Okay, so we've declared our course, declared our low pass filter. Next, we should probably just get down our actual logic here in the audio callback, and then we can start mapping everything. So this is actually much simpler than even the distortion was, because all we're doing is using that process function that both of these have. And pretty much all you really do here is control like the overall signal flow and like amplitudes of dry wets if you want a knob for that or something. But yeah, I can just take, first off, let's take our in0i and put that into our signal variable there. And now I can take signal, and now here's like those signal flow kind of stuff. Do we want the filter to be before or after the chorus? I think I'll probably do before. I feel like that makes sense in my head. So I can just say low pass filter process and then signal. That's it. That's literally it. And then here I can just say signal equals chorus dot process signal. That's it. Because, you know, here, this is like pretty much the same thing as doing this, but it just looks a little bit cleaner because, you know, you're processing signal, and then this is actually returning that, this function. You can see here that it is returning a float. So then that float is getting put back into signal. We take this and we put it here, which then is being processed by chorus, which then this also is returning a float, which means it is spitting back out the process stuff into the left side, so into sig. So that sig variable is now our chorus. So then I can just say out equals sig. And we're done with the chorus. Obviously, we got to map stuff, and there's a little bit more, but it's that simple, the DaisySP stuff. You could literally combine this to like one line of code if you wanted to, but might as well, since it's simple. It's honestly a good reason to just kind of write it out. Some people also, you could say, you could have another variable here, one that is like chorus wet and low pass filter wet, which you definitely want to do when things get more complex. But for the sake of this, it's simple. So this works. Okay, so I am actually going to set default values for this, even though I didn't before. I don't really know offhand what'll work well. We'll say that just so we don't have to map anything and we can get stuff sounding good. And then I have to go set those here. All right, let's see. So as you can hear, there's definitely a chorus going on there. My values are obviously a little bit strange, but you can especially hear the delay. So it worked, and it was that easy. And all we have left to do now is map our stuff, and we will be good. So let's go down here and sort of determine, and I'll show you how to do exponential curves on your knobs. So I'm going to do the rate, depth, and cutoff. Maybe cutoff I could change, but I don't know. It'll probably work. So we just do rate equals, and this is where we can use this fmap function, which, as you can see, it maps a float between a specific range using a specified curve. So it can easily do the simple like math that we had done, but then better than that, we can make it exponential or logarithmic. So first thing we do is say the in, which is that hardware.adc.getFloat. I'll say knob1. And then we go to the next thing. We say what minimum value we'd like. For rate, I'm going to do 1 to 5 and see how that sounds. And then here is where we do what curve we want. I'm just going to set exponential so we can kind of play around with that. Oh, this should be uppercase. And then let's do depth. Depth, I think, is just 0 to 1. So I'm just going to keep it as that, but we'll do exponential. And then cutoff, I think, would make most sense either linear or maybe logarithmic, because this is a low pass filter, so lower values will be more muted, and exponential wouldn't really make sense because we'll mostly want to be in the high ranges. So it might work to just do logarithmic. But I'm also realizing I do not have a third knob set up. I totally forgot I had the pod, so for now I'm not going to hook up a third knob, but you see how easy it is. Luckily the cutoff isn't as important, so let's just go under here and let's say set, frequency, LFO frequency, rate. All right, I'm going to hook up my guitar this time instead. All right, here we are. I have the guitar set up and both knobs are down, so shouldn't really be hearing much, but hopefully I think this is rate and then that should be depth, so we'll keep it lower. Yeah, here we go, we have a chorus. I mean, that's it for the DaisySP library. You could literally have done this with the pitch shifter, a flanger, anything, and then you could have now take a pitch shifter that you're feeding into the chorus and then throw that into an overdrive. It's really that simple before you want to start making your own effects from scratch, which I definitely recommend. I feel like when I first learned this, I was in college and I definitely sat around in DaisySP world for a bit too long, but it does still create some amazing effects. So I highly recommend it. Before we move on though, I do want to add a bypass switch since the final pedal will have that and it's really simple to add. And then for now, I'm just going to hook that up to the LED that is on the Daisy by default that we had used earlier. I normally don't like to touch that and we could hook up an LED, but it doesn't really matter for now. So in terms of hooking up a button, like I had mentioned earlier, that's something that we will be hooking up just to the D stuff. And then for me, I'm using the Daisy pod. And if you have a pod, then we can see here, these two buttons are D27 or D28. So you just can pick one of those. So up here, I can just say switch. I'm just gonna say foot switch for now. So we'll just act as if you have a foot switch, and maybe you do. In terms of hooking that up to, like I just said, you plug in to the D, but it's just 2 pins, a switch typically. So the other one just goes to ground. And you can look at schematics. Some will have more pins. Some pins might just be for stability. Some you can have different sort of places or different states, but you can kind of read the schematic, and hopefully yours just has 2, so you can just plug them straight into that. Okay, so we want to come up here and add just a bool that is our bypass I like when pedals start bypassed, so that's up to you. If you want to start it when it's on, bypassed is obviously when the pedal is off, or it just means it passes the signal, so there won't be chorus on it or whatever effect. I like when that starts as on, when you can't hear your effect. So I'm just gonna, by default, put that to true. And then we want to initialize our switch, so I can just say foot switch dot init. And then we want the pin, so I have not added that yet, so I can say define switch. I'm going to write D27. And then coming down here, I can just put switch. So if you come here into the libdaisy documentation, you can search for switch and we'll see it here. This is our switch. So here are all the different methods. We just did this init one with the pin. And then here are all the different ways that we can kind of get data from them. You have falling edge, pressed, rising edge, and these are just all about like what state of it being pressed is it at. Falling edge, you can just click it. True if the button was released. So if you hold it down, then that gets triggered the moment you let it up. Rising edge should be the opposite of that, right when it's pressed. Pressed is obviously like while it is being pressed, or if a toggle is on. So if you have one that is just switching to two states. Debounce is what you call in whatever kind of function that you're actually checking for. So if you were checking for this in this main that is always looping, so down here you can see this is always looping. I know I said this is called once, but then there's this while loop that is always looping. So you could call debounce in there. I'm just going to do it within this process ADC. So I can say foot switch dot debounce. I'm not sure if one is better than the other. In the examples codes, I've seen people do both. I'm not totally sure, to be honest, but just since we already have all this stuff in here, I'm going to put that here. And then we basically want to say if we are being pressed, which mine is just a single state one, and we're going to kind of treat a foot switch as that. So I'm going to say rising edge, which was like the moment it was pressed. Then we want to set bypass to the opposite of bypass, if that makes sense. So if bypass was true, which it will be in the start, then when you press it, what do I keep doing? When you press it, we want it to just change to the opposite of that. So that's all you got to do. There are a couple other ways to write this. One way that I really like that a lot of people don't really use are the bitwise operators. So I can say bypass and then the little caret equals foot switch dot rising edge. This is this either or not either or, like this exclusive or, where basically if both of these are the same value, this will return 0 or false. And then if both of them are different, then it will return 1 or true. So you can think of this in the beginning, how bypass will be true or 1. And then until you press the button, this will be 0. So they'll be different. So this will just keep being 1. And then the moment rising edge is pressed, this will be 1. And then this will be 1, and then that means that this will be 0 and turn to false. Kind of confusing, but just know that you can write that and everything will work great. And then what we can also do is set the LED. I can go set LED to, we would want the opposite of bypass, because if it is, you can think of a pedal, when you turn it on, you want it to light up. So when you're not being bypassed is when you want it to light up. So we can just set it to the opposite of that. And then up here, we have all of this processing code. And we basically want to say in the end that if you are bypassed, just simply be the output. So we could do something like if bypass, then out equals in 0i, and then else 0i equals sig, and that's all you need. Or you could use the ternary operator. Yeah, let's try this out. All right, so here's the pedal, and like I wanted it to, it is bypassed from the start. Mine is hooked up to this button, and now we can hear the chorus. And you can see this LED here that is changing with it. One thing you'll notice is a pretty big change in volume when I turn the bypass on and off. That's because some of these processings will kind of, have certain volume changes, so it is pretty normal to just apply some makeup gain. You could honestly even define that up here, or just have some big variable of makeup gain that you're always applying to this end thing here, like 1.5 or something is typically fine. So you can play around with that, but that is pretty much it. Later we will add the LED code and get this, we'll have to change where everything is hooked up to and all that. But yeah, I mean, that's like genuinely how you do 80% of this stuff when you're just using the DaisySP library. It really is that easy. And if this is really complex for you because you're just learning to program, I promise that if you just spend some time getting the basics of any programming language, then this will be much simpler, because all of this stuff, like you can really ignore a lot of it, and then the rest that you shouldn't ignore is all just in plain English, and as long as you know the kind of audio terms, then you'll be totally fine. All right, so to start, we are going to make our drill template for the Tata Electronics site, which pretty much means that we're going to decide what layout you would like for your pedal. I'll go over some limitations and things to keep in mind for that, but first we get to pick out which enclosure you would like to use. So here I am just on the Tata Electronics website, and we're going to go down to hardware and then enclosures. So here you can see there are all these different sizes of enclosures that you have to pick from. They range in price, and I think they're all pretty much the same material. They're all just aluminum. And then we come down here and you can see you can get them in just a solid color. So definitely take some time to scroll through here, but I would be cautious because some of the sizes for these in the photos look very deceptive. So definitely go in and check the actual dimensions. Like for example, you can see here is the 125B, which is the one that I ended up using, and then the 1590B. And you can see in these two photos, they kind of look the same size. If anything, this one looks like it's maybe a bit wider. But then if we come over here to my desk, this is a 225B and this right here is a 1590B. And as you might be able to see, the 125B is quite a bit larger, and more specifically, it is much taller. So you really want to be careful when you're looking at these, especially with height, because with our Daisy, it does take a good amount of height. So something like this is quite easy to fit everything in with the knobs taking up all that space in there, and then the Daisy. So something like this, you would have to design it much more smart to be able to fit everything in there. So that's kind of why I choose the 125B, is so it can fit the Daisy really nice, and it just has a little more surface area than the 1590B. So if you're trying to do something with like 4 or more knobs, or maybe some knobs and some switches, or 2 foot switches, then you'll definitely want something bigger than something like the 1590B. But this is a great option if you're better at fitting everything in there and you want maybe like 2 to 3 knobs can fit really nicely in here, and then it will kind of give that really nice sort of boutique, because the small pedal is quite nice. And then they do have much larger ones if you're wanting to do some sort of really big multi-effects thing with a ton of knobs, then that's super doable. But once you find out the enclosure that you would like to use, definitely just type it in here to search it so that you don't end up getting one with all the different colors if you don't want that. So like here's just the base 125B, which comes in about $5.50, and then if you want, you can go and look at the colors and stuff. It only adds an extra 50 cents for powder coatings here, but also to note, like if you just want color on the top, that is UV printing and the graphic stuff will do. So this is just if you want obviously just the whole pedal to be a different thing, and then we put the graphics on top of that. But this has nothing like directly with the graphics will do. I mean, you'll have to do stuff with colors based on the enclosure color that you use, but it's not too big of a worry, and you can kind of worry about the color after we make your graphic and everything, because you won't really be ordering any of these parts until you have the design with it too. So once you have the enclosure you would like to use picked out, next is just to obviously think up the amount of knobs, switches, and everything that you would like to use. You can either just sort of draw this out. Maybe you're a graphic designer and you sort of do that first, or that's how you think, or maybe you just have a pedal of your own that you would like to replicate. Any of that works. Just sort of think that up, and then we're going to head to the Tata Drill tool. So you can search Tata Drill, and then they have this really nice place where we can make these drill templates here. So it'll show up with the enclosure types here. So you can just pick whichever enclosure you would going with. And here's maybe also a good place to see all those sizes just quickly, You can see which ones are the biggest nicely. So this is just so we can give Tata a little document saying where we want all of our holes to drill. So we don't really have to use any tools to drill stuff. If you do have like some sort of drill press or something, then obviously you could just do this on your own. But say you wanted to order 50 of these or sell anything more than that, or maybe just make 10 for friends or something, this would save a lot of time, and it's really not that much money. We can see in Tata, you can search drill here, and here you can see all the drill services. You will have to sort of add this to cart in addition to the enclosure. I'll show you all that later though, so you don't have to worry about that yet, but you can see they're all the same price, so it doesn't really matter if you're having a big or small. This will cover up to 40 drill points, which is a ton, so you're probably not hitting that for your first pedal or anything. And then you can see it also gets much cheaper the more you add. So it is more than half off if you get 50 plus, if you were to actually sell some. So back to the drill tool. The next thing you'll need to do is figure out what sizes the diameters of the components are, quite obviously. This is also pretty simple, but can be somewhat like nerve-wracking if you don't have the part sitting in front of you, because obviously if you got the holes wrong and they are too small or maybe way too big, then that whole enclosure you will need to rethink after you have already ordered it. But luckily it's really not that hard to make sure your values are good with plenty of clearance for them to fit. So there is a couple ways to do this. One is if you don't already have your parts on Tata or whatever you're ordering your parts, like here is where I think my knobs are from. Yeah, these are the knobs I use. So you can see here, this knob has a shaft diameter of 6 millimeters, which you might think that, okay, that's our size, 6 millimeters, but there's a few definitely wrong things about that. One is that you obviously need to add an extra bit of space. And then in the case of this knob, the shaft is this top part that you actually turn, but you'll see this bottom part with where you screw the nuts and washer onto there, that is clearly sticking out much more. So 6 is not going to cut it at all. So 6, even with a little bit of clearance, will probably not be able to fit this extra part there. But you can see that right below here, we have mounting hole, 7.5 millimeters. So that is probably the answer. We can come in here to the data sheet and see a little better everything. So yeah, they have mounting hole detail and they just very nicely tell us this means diameter. So we have a 7.5 diameter, and you can confirm that. Like here we see this washer, which we know fits over top of it, and that has an inner diameter of 7.1. So clearly this 7.5 is giving us that clearance already of about 0.4, so that should work great. There are definitely times where it just won't nicely say mounting hole. For example, this is the foot switch that I use. And by the way, all of the SKU numbers for all of these Tata parts, I'm going to put in the sort of GitHub documentation of this whole course in the description. So don't worry about having to type this in and find them all yourself. You can go there and they'll all be linked. But here you can see there's literally not a single thing talking about the diameter of anything. But if we click the data sheet, you can see they have this very minimal photo just giving some basic measurements. And then right here, we can see they show the inner one is the diameter 8.5. And then we have this M12X1. That's just referring to the actual like bolt or screw. So the amount, so like the thread length here is 1 millimeter and then the diameter is 12 millimeters. So this would be nice to know what type of nuts you would need to put over it. But for our case, we can probably just assume that 12 millimeters would be okay, and you could add a little bit on top of that. I know with this foot switch, I think I do 12 millimeters because I just measured it after I bought it, which I can show you in a second. But it's kind of not as nice, obviously, as just seeing the mounting holes, but it should be fine. I'll talk about sort of the recommended amount of clearance to add based on what you might see in data sheets or measuring it yourself, which I will show you right now. All right, so here I am with all of the parts that I just showed you, the pot and the foot switch, and here's a jack that I use, and calipers. This is a pretty must-buy tool if you're going to do stuff like this. But yeah, you can just really nicely measure. This one's a digital caliper. It's only like 10 bucks or something. And this would be really handy because I can take something like this knob, put it right here, and then I typically add about 0.4 to the value here. So this knob, I'd probably go and do 7.2, which adds up with the, I think 7.5 that Tata said it was. And then you can see if I were to measure this top, it is about 6, just like it said on the data sheet. Same here, I think we said 12 for this one. So if I measure, you can see we're just about 11.6, a little more, a little less. So that 12 makes perfect sense. So coming back to the drill tool, make sure you have written down or know those numbers of all the diameters. And then here we can just go about placing everything. A few things to note with sizing. Say you were to try and make like a 6 knob pedal or something, then you definitely want to know the measurement of the overall part. Like say you wanted 6 knobs, then here with this knob, you would want to really know that like this whole diameter is 16.9. So you want to make sure that when you place it near the edge, you don't totally push it over the edge there. And also keep in mind that in the corners of all of these boxes are little screw holes. So I wouldn't shove anything like directly in the corner, especially when we are fitting the PCB in there. We're not going to have the PCB fully just stretch out to be the size of this perfectly. You know, you could have a little cutout for them in the PCB, but I just wouldn't go around throwing things in the absolute edges. But if you're just looking to do a 3 or 4 knob thing, then should be pretty kind of intuitive of just placing them nice and even, not too far back or close to the edge. Theta is a little bit strange. As you can see here, the 0, 0 position is in the center. So everything we do is just going to be offsetting that from the center. So a positive X will put you to the right and negative to the left. And then same thing for Y, positive will be up and negative will be down. Here you can pick what side you would like to put everything on. All of the sides except the lid are included in the base drill template, like that initial cost. But if you do for some reason want to add holes on the lid, then you will need to buy a separate service. Theta also somewhat recently in the past few years added these awesome abilities to do lines and shapes, which honestly is pretty huge. Like if you want to do something like a little screen cutout or something, then you can really easily add that, or some sort of cooler LED pattern or something. You can really easily do that now and it'll just be included in that base drill template. So just as an example, here is the pedal that I ended up making. I will put a link to this template in the GitHub so you don't have to recreate it if you're making this pedal. But yeah, you can pretty much just see everything we talked about, like 7.2 diameter is what I ended up doing, 12, and then just sort of spacing them out nice and symmetrically, which having it be symmetrical isn't like required. It might make your life a little bit easier when it comes to making the actual PCB, but not really enough that you should totally make the design around that. So the main big design limitation when it comes to dreaming up your pedal is the actual Daisy. We can see here the Daisy is 51 millimeters long and 18 millimeters wide. So you need to make sure that when you are spacing out your knobs that it accounts for that. For the most part, if you're just trying to do like 1 to 4 knobs, I would say you can just think up your pedal and then imagine where the Daisy goes afterwards or when it comes to the PCB, and then you can always come back and sort of move things around. But if you're trying to do like 6 or more knobs, if it is this enclosure, obviously if you have one of the big ones, then it doesn't matter. But if you're trying to do like 6 knobs, then you're gonna have to think that out. Like if you were trying to place them in this cool, like a regular design, that's gonna be a little bit tough. If you want them to just be symmetrical, like here, for example, the Daisy is horizontal. I'll show you actually the insides of the pedal in a second so you can sort of see what the final product's gonna look like when you're imagining your knob layout. But yeah, here it is horizontal. So I basically need to make sure that there is those 18 millimeters in between each hole. But the thing is, the holes aren't exactly where the pins in the PCB are. As you can see with this knob, the actual center of where the hole is about 16.5 millimeters from the pins. So what that means is that the hole might be here, but the actual PCB is here. At the end of the day, you can still sort of think of it as the distances between these two, because obviously just in this case, the PCB actually starts or sort of ends around here. And then the Daisy is going to be sitting probably right here. But yeah, you need to make sure that you remember that and have that in mind. Like in this case, I could not put a knob right here because then those pins would most likely be right over the Daisy, which also can be okay since the Daisy will have these headers, meaning it is sort of raised up. You can actually put and solder things in the middle of the Daisy, but you would need to make sure that it's not directly stepping over the pins, and it just adds a little bit of complexity if you do have all of these pots and components in the middle of the Daisy. But yeah, that's pretty much all in terms of the drill schematic. I will say there's a high chance, especially if this is your first time doing this, that you will be sort of changing this as we make the graphic and the PCB. So I wouldn't worry too much about it. I would mainly just know how many knobs you want or switches or LEDs or anything. And to just make sure you know which parts you're going to use. You don't have to have like all the specifications written out, but you will be needing to refer to them quite a bit as we make the graphic and especially the PCB. All right, Sam from the future here. I realized after filming this that I forgot to mention anything about the audio jacks up top here. And it's pretty simple, but there are just some things you want to remember. First off, you obviously have all your different sides you could place them. The typical ones are either on the top or on the side, the right as the input and left as the output. For the 125B enclosure, I probably could fit the jacks on the side here. I just kind of like them at the top personally, and I like when they sit sort of cleanly with the DC jack. If you are doing the top, the one main thing you'll need to remember is the screw holes. So if you had something like a 1590B and you wanted to do a setup like this, that's going to be much tighter, and maybe really thick audio jacks like this aren't going to work. The other thing you want to be mindful of are the actual potentiometers that will be below your audio jack, so you can see the potentiometers under there. And to be clear of that, I just didn't put them center. You know, you have them up a bit, which then you would just want to check the data sheet for whatever jack you use. They're much smaller jacks than the ones I have here. These ones are just pretty cheap on Tata. But yeah, like everything else, you're going to want to cross-reference with the data sheet and the measurements and then your actual enclosure. Like I said, there's much smaller jacks. So like here is the 1590B pedal, and yeah, it's facing this way, so the PCB will be here, and then I actually just put the jacks down here, and these are ones that have a much smaller kind of overall size there, so they can go pretty tight. They could even probably fit nicely in a 1590A, which is a little bit smaller. But yeah, something like this, these would be kind of tight at the top, so I just decided to mount them on the side, which a lot of pedals have them on the side too. Especially if you wanted to do like PCB mounted jacks. They're pretty easy to do. You just got to be kind of mindful and make sure you buy ones that you can slot in flush, and then we'll kind of put the screw thing from the outside. I don't have any on me right now, but there's ones like this one right here, which protrudes out, and this wouldn't be good because if I were to unscrew this, if I were to have this on the edge of a PCB, and then obviously if I slot it in, it'll just hit it there, and that won't really work. So make sure to get ones that do. But yeah, if you're using like the 125B and you want them at the top, these values work great. So you can just copy these B-side ones. And if you want them to be on the sides, just be mindful of your foot switch, but you can always put the foot switch kind of parallel with the jack so that it won't interfere with each other, and it should be all right. But yeah, that's about it for the drill tool. So what exactly is a PCB, and why would we want to make it for a guitar pedal? Here you can see I have a couple different pedals, and you can see the PCBs in here, which stands for printed circuit board. So far in this course, we've been using a breadboard to do all of our routing, which to do it, we would have to put the seed down, and then say we put a knob, we then have to connect every single pin with wires. And that both takes up time and it takes up a lot of space. So obviously if I wanted to put this inside of there, we would have wires flying all over the place and it would be such a hassle. With the PCB, we are able to specifically do all of the routing within a software and then cater each PCB to a specific circuit. So as you can see here, we have the 2 rows of 20 pins for the Daisy. These are for the pots here, and then the foot switch and everything. And so all we'll have to do is solder on the parts and not have to worry about the routing at all. Here you can see in all the pedals you get, this one's just the Electro-Harmonix Big Muff. You turn it around and you can just see the PCB right in there and all their parts, which is a pretty cool way when you're starting off to just see how some of these pedals look. Here's an example of one without a PCB. This is one of the first pedals I ever did, and it was made on one of these proto boards, which is technically a PCB, but it's just not a specific one with a circuit. And we can see all of these wires in here and this horrible, ugly soldering that I grouped up everything. I really had no idea what I was doing. But yeah, it was a little bit of a hassle to do, always a hassle to fit it inside. And so making a PCB makes it so we can just have everything sitting nice inside of there. You can see here I still have all these wires, and that's just because I didn't use PCB mounted jacks and foot switches and stuff, just because when you're starting out it's a little easier to not have to worry that deeply about space, but it is a nice way in the future to get it so your builds can be much smaller. Another great thing with PCBs is that they end up actually being quite cheap. We're going to be designing 2-layer PCBs, and on PCBWay each one is only going to be $1. You can't order a single one, so you have to order in 5s, and there'll obviously be shipping. Typically the the sort of global shipping is around $5. So it'll be 5 for about $10, but that's an excellent price. And if you want to buy maybe 10 and make 10 pedals, then the price will only get cheaper as the shipping price will get dispersed through all of those. The software I'm going to be using to design our PCB is KiCad or KiCad. This is a great open source software, so it's a great place to start, and you can just search KiCad and download it here. Depending on when you watch this, there might be new releases. I'm going to be using KiCad 8 because it's what I've been using. And honestly, most of what we're going to be doing is a lot of these sort of primitive features, so I don't expect it to really change a lot if you're in a later version. So once you're in KiCad, you can come up here and hit new project. I'll just name this chorus pedal. So it might be kind of confusing at first. There's a lot of sort of random symbols, and we're going to get to some of it, a good amount of it. But for now, the main thing that we are going to be doing is adding symbols. There's a few kind of terms in PCB design, especially with the circuits. There are symbols and footprints. Symbols are the actual symbol that we'll use in the schematic here, and then footprints are the sort of pin layout that we will have on the PCB itself. So like for our 3-pin knob, that will have a footprint with the specific spacing that the datasheet tells us, and we can either make those or find them online. I'll show you how to do both. So to start, you can hit A. This is where we're going to find all of our symbols. They have a huge library of kind of all of the typical parts, and luckily for us, even some very specific microcontrollers like the DaisySP. So you can just come here, search DaisySP, and it should pop up right there. This was added in some recent year. I'm not really sure, so it might not be there if you have an earlier version, but you can always just Google it and find it online. So then you will get to place it. I'm just going to place it up in the corner here, hit escape, and now we have the Daisy. So hopefully by now you are able to somewhat recognize what exactly this is, but this is just this exact pinout right here, just sort of organized in a way that's a little more helpful for designing our actual schematic. But as you can see, we have like VIN, which is up here, and that says pin 39, and then down here we see VIN is 39, and that'll just be true for everything. So nicely they have all the power at the top and then the 2 ground pins at the bottom, which is why this is laid out that way. But you'll see that the actual numbers just totally coordinate with this pinout right here, which I do recommend just going forth with designing this, that you have this photo open somewhere, because we will be referring to it a pretty good amount. So next, we probably just want to add all of our symbols, since by now we sort of know what exactly we want. In my case, I have 3 knobs, a foot switch, and an LED. And then with that LED, you will need a resistor. Typically 1K works good for a Daisy, so I'm just going to do that. So if I hit A, I can search potentiometer, and then this is where you will want to sort of go through and make sure it's exactly what you need. We know that the potentiometers we've been using, they have 3 legs. So right here, we can see that this will probably work just fine. And then I could just go 1, 2, 3. I'll explain what everything means about this once we get all of our symbols set up. But next, I'm going to go and just search for an LED, and there we have, that's sort of the default LED symbol. Then I'm going to go and get a resistor. I'm going to use this US one because it's what I know. You can hit R to rotate, so I can just immediately line this up with the resistor right there. Make sure the resistor is attached to the correct side of the LED or your circuit won't work. So here it should be on the side where that arrow is pointing. And then next, I'm going to search for a switch. There are typically many different types of switches that, as you can see, will have so many more basically switches within it. Your typical one will be the SPST, single pole, single throw. So make sure that that's the part you bought, if that's the one you're wanting, if it's just an on-off sort of switch, or if you ended up buying a different one, then you can find a symbol that matches that. But I'm going to just do the SPST. The other things we'll be needing are the audio jacks. So I'm just going to type audio jack, and here it is. So we're just going to place 2 of those down, and then we'll just need our DC jack, and I'm just going to place that up here. So a couple quick things about KiCad. One thing that's sort of specific to KiCad is when you zoom with your mouse, it'll zoom from wherever that point is. So you can see I'll place this, and now I will kind of jump over there and zoom into that. It's actually quite handy, to be honest. And then also, when you want to select a specific object or like move it or something, there are all these shortcuts, and if you just hover over it and I press M, for example, I will now just be moving that exact object or symbol that you were hovered over. Same thing with like E to edit. So you don't have to click and then hit E. You can just hover over something and click it. And say if you're moving, for example, I can hit escape and it'll just pop right back to where it was. So I'm not really going to get into much circuit analysis or really explaining much, because honestly, we had already sort of done all of this. We already routed everything on the breadboard, and we're going to do just exactly that once again. So I'm just going to show you how exactly we route things, how we can connect all of these wires without needing to draw them all around the screen here. So we could just start over here with the Daisy. First thing we can do is sort of just define that these are our ground, and there are some nice symbols to do that. So if we hit A, you can actually search for ground, GND, and there will be a symbol for that. So then here we are with ground. I can just connect both of these to that. So now these are both connected, and then that means that whenever we place another ground, that will also be connected to this right here. So now I can come over to these pots, and if you remember, there's those 3 pins, the middle one being the one that goes into the Daisy, and that just goes exactly like left to right here. So 3 was the one on the left, 2 is the wiper, the middle one, and then 1 is that one on the right. It's not a huge deal if you put them sort of backwards or anything. You can always in the code just invert the way the knob turns or anything, so you don't have to worry about it that much. But I'm going to connect all of these downwards to a ground pin. So then here, those connect up. That just means that these are all connected. I can hit A, ground, and connect that right there. And then this top part, if you remember, actually gets connected to this 3v3A. So we're gonna need some sort of way to make sure that we can get this signal over here. So over here, let's see and search if they have a 3v3. Yep, here it is, and then I can just connect that right there. The shortcut to get the wire tool is W, but that will start creating a wire from right where you hit W, or you can also just hit escape, and then if you hover over here, it'll start to draw a wire. So I'm gonna make sure I leave some space because the wipers we're going to have coming out a bit. So if I bring one out there, you can then double click, and then I can bring another wire there, and then our last wire there. So those are all connected, and then we can get that 3v3 back. Oops. And now those are all connected to the 3v3. So the next thing we can do is connect these audio jacks. You can see here there's an S and a T. This just stands for sleeve and tip. Sleeve is typically ground and tip is our actual signal. This is also a way that you can look on your jack to know which one is ground or sleeve. You can Google that and it should pop up. But yeah, we want our tip to actually go into our audio out. So I'm going to do the ones as that. So there is 1. It is nice to try and keep things a little straight. So then we're going to put the audio in 1 there. Probably going to move this back just a little bit so I can add our grounds here once again, and then we can rotate that around. So boom, boom. And now our jacks are connected. So next we can do our jack. This symbol right here usually means ground, so I can put the ground there. And if you ever see a symbol you don't know, you can easily, like here, you could Google DC jack symbol meaning or something, and it should pop up. And then I'm going to connect that to our V in. Up to this point, you might have not actually used a DC jack yet to turn on the Daisy, but obviously if we're making a pedal, you don't want to hook up a micro USB or something into the Daisy. So we're going to be actually mounting a jack on there, and you just hook that up to the V in and then ground. You can see here on the DaisySP data sheet, we have the V in range, which is at minimum 5 volts and maximum is all the way up to 17 volts. So your typical like 9 or 12 volt power supplies for pedal boards or anything will work totally fine with this. I always just use some random 9 volt power adapters I have lying around. So yeah, you can just hook those up right there. So another thing we need to do is connect the LED and the switch to ground. So here I can just put ground there and then ground on the LED there. And then all of these remaining pins like on the pot and this resistor and here are all just going to be going to specific ADC or digital pins on the Daisy. Now this is something that for now we can have it routed to a specific place, but honestly you will probably end up changing this to help out with your PCB later, because you'll find that when you place parts in specific ways, then some will be closer to certain, say, ADC pins than others. And so you'll want to just minimize the length of all of your sort of routing. And so we'll want to put that later to the most optimal position. But for now, we can just sort of put them in a standard place so we can get our actual routing worked out. So like I'm just going to put these 3 pots to ADC 0, 1, and 2. And how we do this, instead of drawing this huge wire all the way over there, is we can use labels. So you can see this A with an underline. The shortcut is L. And if I tap L, we'll get this little prompt where we can type in label names. So I'm just going to say pot 1, and then I can just attach that right to any of these ADCs. So I click it, and then that little circle disappears. So that means that this connection is now pot 1, meaning any wire that we then put that label to, those will be connected, and that will also be pot 1. So then I can come over here, click again, type in pot 1, and then we get that, and boom. So now these are connected. You can see that right here when I click pot 1, it says connection name. So that means if I were to draw sort of any wire coming out of here and then click it, you'll see the connection name is pot 1. So now we can go through. I'm going to do pot 2 and place that there, and then I can do pot 3, place that there, and then I can come over here again and say pot 2, pot 3. So now all of our pots are connected, and we can just do the same thing for the switch and LED. So I just have connected those sequentially because, like I said, we'll probably change that, but maybe just for now connect them to something that you know is at least correct, like the foot switch and LED. It says the ADC 3 and 4, but we're actually connecting those to the, like in this case, D18 and D19, but it doesn't matter a whole bunch at this point. So all the remaining stuff we have to do is pretty much just trying to tell KiCad, our software, what our circuit exactly is. So there's all these things that we can tell KiCad so that it can tell us whether we have things correct or not. Because there is this really nice helpful feature called the electrical rules checker right here, which I can hit run, and it will try and tell us if there are any errors in our circuit. And as you can see, it is telling us there are a lot. But it's kind of confusing because we pretty much routed everything perfectly. But we can see here it is yelling about all of these. And let's see what those exact errors are saying. Pin not connected. So it's yelling at us for all these pins that we don't have connected, which is kind of annoying because we don't even want these connected. But they do have a way where we can tell KiCad, hey, we don't need these connected. And that is this little no connect flag, which you can just hit Q. So I can hit Q and it will just place it right where you are. So don't do that, I suppose. But you can just go over all of these and hit Q on them. All right, so I have X's on everything. Let's see what it is still yelling at. So it says input power pin not driven by any output power pins. We can see those 2 arrows on the ground here and the V in. This is basically happening because the software knows that this V in and ground should be having some sort of output power, and we haven't exactly told it that this jack right here is that power, and we need to explicitly do that. So I can come here and just hit A, and then you can type in PWR, and this power flag will pop up, and then we can just connect that to both this V in and the ground. And I know it's getting a little cluttered. You can always come and hit M on the actual text to move it around, or I can obviously just move this jack backwards. So there we go. Now we have told the software that this is some external power, and those errors go away. So now we're almost done, but there is one last thing we need to do. So we told the software here with the power flag that this is power, but this is only for that ERC checker. But we will need another way to tell the software which connections are power, because something like the V in from the DC jack is going to be carrying a lot more current than, say, our foot switch right here. And when it comes to designing the PCB, if something has a higher current, that will need to have a bigger connection width. We'll talk more about that later when it comes to making the PCB, what exactly tracks and things are. But for now, we just need to make our power net class. A net class is KiCad's way of being able to group together these connections. So I can come and hit File Schematic Setup, then come to Net Classes. Then we can hit the plus and just say Power. Next, if you come over to this A right here, you can hit that and then select the Power Net class. And then we can just hit that on both this V in, and then we will want to add it to the 3v3, which I'm going to extend this out just so it looks a little less cluttered. So there we go. Now, if I click this wire, you can see down here we have the resolved net class of power. And that's pretty much it for the schematic. This is obviously a very simple circuit. We added pretty much nothing else except the bare minimum of what we need to get everything running. I definitely implore you to go search more and learn so much more about circuit design and things. It is a little over the scope of this course because I'm just trying to teach you how we can get this bare basic pedal where you can start programming everything, but there's a lot of room for stuff here. A great way to learn is look at other people's projects. There are things like even Daisy stuff like the Daisy pedal or that terrarium PCB I mentioned, or there's other open source projects where you can go and just look at people's schematics. So for example, here are the build documents for the terrarium PCB, and we can see here this is their schematic. And there's a lot more going on because obviously they have more switches and things, but also they have all these little circuits which are in between typically just the jacks and into the Daisy, and then your DC jack and into the Daisy. These are things that are just going to help with voltage regulation and noise suppression, which is definitely a must if you're trying to sell a lot of these or really try and make them as professional as it can be. But for now, this will totally work and was pretty easy to set up. So there's one last big thing that we have to do, not exactly on this circuit, but on all of our symbols to then prep our PCB. I mentioned this before, but these are called symbols, and then on the PCB we have what are called footprints. We need to have each symbol connected to a specific footprint, so once we go into the PCB designer, it will, for instance, know that this pot 1 is the specific 3-pin layout that we have for the specific knob that we are going to use and purchase. There are a lot of standard ones like your resistor and LED, but we will need to find or make ones like our knob. If we come up to the top menu, you will see this footprint editor here. You can click that and you will see all of the different footprints they have. They are sorted into all these different categories. So like a capacitor, and this THT means through hole, which is what we're going to be doing for this. The other option is SMD, surface mount device. You will typically see surface mount stuff in professional pedals or just all PCBs of all kind. But since this is something that is just like if you order for yourself and you want to solder, through hole is much easier to solder. And in the context of the pedal we're making, which is super minimal, we don't really have to fight for any space, so through hole is totally fine. Here you can click around and see all the different footprints, but I have been having this unfortunate glitch where it just doesn't show anything. I knew there was some way for me to get around this, but it should work for you, hopefully. And it doesn't matter a whole bunch at this moment because there is another way to view it. So if I close that and then come up to this symbol, this is where we can actually assign each symbol to a specific footprint. So like here we have this LED, and then on the left are all the different footprint libraries, so those just overall categories, and then we can come up here and filter it by specific things. So like this first one will let us filter it by the footprint filters defined in the symbol. So that is definitely a really handy one to do. So like if I had none on, you can see we just have every single footprint here. The default library with this version comes with 1180 footprints. And then we can also sort by pin count, which is handy. So the software knows that this LED is only 2 pins. So there's no reason for all of these ones with like a ton to pop up. So I just filtered by only ones with 2 pins, and then you can also hit here to filter by library, which then I can type that in right here. So I'm just going to filter by all of them, and then you can see here we have just a pretty small list of LEDs. The LED that I am going to be using, which is kind of the typical one you will get, has a diameter of about 5 millimeters. If you have any sort of basic kit, that's probably also what you have, but as always, make sure you check. But I'm just going to come here and make sure we are looking at the LED through hole, so the THT, and then you can see all of these different sort of measurements. They're a little annoying to read, but they are pretty self-explanatory. If you see D, that is the diameter. And then in this case, the horizontal is probably, yes, because this footprint is meant for having your LED that way. We're not going to have it like that, so I wouldn't worry about that. But right here, I already just see this D 5 millimeter. So I'm going to click that, and that looks exactly like what I want. So I can just double click that. And now that is assigned to the LED here. And also we can see that the Daisy already has assigned that one footprint to it, because the Daisy, obviously there's not all these different ways that you can pick from. So it already just assigned it. Now, in terms of our audio jack and DC jack and even the foot switch, all of those are going to be just hand soldered and wired into there. Unless you chose to do ones that are PCB mounted, then hopefully you can figure out how you're going to do that. But in my case, I just selected to do hand soldered ones just because it's a little bit easier to do the PCB design, and it honestly is higher quality because having PCB mounted components just give a lot of extra stress onto the PCB, and they're a lot harder to replace if something were to break, because obviously you can just unscrew and rewire a simple jack. but you would have to take out the entire PCB and desolder every single pin in order to replace a broken one that was soldered onto the PCB. But in order to get some connectors that we can just solder onto there, we are going to need to go to the connector library. So that is right here, and then I can hit connector, and we do actually want to hit the library on. So we're just on this connector here, and I can already see that this is not exactly what we want. These are sort of very strange connectors. So this is something where you can just look and be like, okay, that's not what I want. So we can go down and see that we have this connector wire, which is what we want, because we're just trying to connect some wires. So now we have this very big list of all these different wires. So first thing we want is just to hit pin, so we can just only have everything with 2 pins here. And now we can read what this has to say. So like all footprints, there are all these different measurements here, but these are pretty self-explanatory. This first measurement is pretty much your wire gauge. This is in square millimeters. You can search any chart on this, but 0.5 square millimeters sits around your 20 gauge, which is pretty much around what typical wires that you will pick up for this sort of thing. So now we can just see all of these 0.5s here. So we're going to need one of these. So then this second one is just saying how many pins there are and how many rows there are. So this is 1 row of 2 pins. All of these are going to be 1 row of 2 pins since we sorted by pin. And then the next one is pitch, which is just the distance between each pins. Typically something like a proto board with just all your pins and PCBs are designed with about 2.54 millimeters spacing. So that's just a good reference point. Something like this is a little bit bigger, which is just going to be like a little nicer to solder. So there's less chance of like solder bridges or something. And then right here we have the diameter of the actual hole. And then we have the outer diameter, which factors in the size of the pad that we will be soldering on. Then you'll also see these ones with relief, and if I go and select these, you'll see that they have just this sort of long thing and then another hole, and this is basically just a way to make sure that your wires aren't putting too much strain on the actual joints if they're kind of being moved or stretched around. So it's a way to just kind of hide your wires and maybe route them through that or add little like zip ties. Sometimes people do, but we're not going to worry about that for now. So it's looking like with this gauge of wire, our 2 choices are pretty much just these 2, and you'll see this one just has a slightly larger pitch and a larger outer diameter, meaning the pads are just a little bit bigger. But I think that this first one here will be totally fine. So I can just double click that for this jack, and even the DC jack will also take that one, and our switch. So now we only have 4 things left. First, we can just deal with this resistor here. So once again, we can go and make sure we are sorting by the resistor library. So we can come down, find the resistor through hole, make sure your pin thing here is checked, and now we have all of these different resistors. Your typical resistors are those axial ones, so we'll want all of these here. So resistors, like everything, have their own sort of little codes. Your typical resistors are going to be the axial ones, so we can ignore these radial bucks and all of these other ones. And then you'll see these other little codes, and basically this stands for the overall diameter and length, just sort of roughly. So this DIN 0207 means it is roughly 2 millimeters in diameter and 7 millimeters in length. But then you can see this then classifies even deeper than that. So this one is for 6.3 millimeters and 2.5 in diameter, and then a pitch of 7.62. And then you can see they have vertical variations. So if you want your resistors to be kind of standing up like some people do, you can do that. But we're going to have just the horizontal sort of long ones. You're of course welcome to measure out the resistors you have and everything, but I happen to know that for the ones that I have, this footprint right here works out great, number 8. So now the only thing we have remaining are our 3 potentiometers. So you can see here when I sort and go into the potentiometer through hole, there are some that might work if you have them, but for the most part, especially if I go and look at the exact one we bought and see that the manufacturer is Tata Electronics themselves, we can probably assume that they do not have this on there. So there are a few things we can do when we see that KiCad does not have the footprint we want. The first one is to just find and search for this part number and see if anybody has done it online, or we can make our own. In the case of this knob, if you were to go and search it, you will find a few 3D models, but there is no specific footprint that pops up immediately because honestly, it is a pretty simple footprint that we can go and make ourselves. So I did realize the knob that I actually got was this 10K one by Alpha. Pretty much the same thing, but yeah, we can make this ourselves quite simply. I'll honestly probably go through it somewhat quick because there are many tutorials on how to do this also in KiCad, But make sure you get your data sheet up. You can see that this one, if you remember, the other one had a 16.5 difference between them, but the ones I have 16 millimeters between the center here and the pins, so that's definitely really good to know. And then we can go and kind of just read here. A lot of this we don't need. We really just want the distance between this hole and the pins, which we needed for making our drill schematic. And then the other main thing is just the size of these pins themselves, which this is that sort of mounting hole detail thing here. We can see all these circles, which are just pretty clearly this right here. We can see there's 5 millimeters between each one. That is something we'll need to know. And then it says there are 3 with a diameter of 1.2. These are all in millimeters. That's quite standard. So we just know that we need 1.2 millimeter holes. Typically, if something says mounting hole, then that means that that's the actual size of the hole that we will make. So we don't really have to add clearance on top of that. Typically, there might be exceptions to that. I've always found that what they say here is pretty much good. This is typically given for the point of making footprints and things. So yeah. All right, so I'm back here in KiCad and we need to make our footprints for this. So what we can do is come up here to the edit, delete, create, edit footprints. And then mine started working again. Suddenly I can click it unlike earlier, but we can just come up to this top left thing here to hit a new footprint. You can name it probably just the part number. I think mine was the RV, 164A or something. RV16AF. Okay, so I'll just name it exactly that, just so we know. Or you could just say potentiometer, make sure to select through hole in the case of this, pot or SMD if it is, obviously. So there's a few things here. We haven't gone over what all of these layers are yet. We will get to that when we start our PCB. For now, we can somewhat ignore them. The main thing are pads. Those are going to be the actual pins that we will make and solder onto. And then there's a couple other things with the layers, but I'm going to have right next to me, I have another monitor that has the mounting hole thing up. So definitely good to just have that referenced. And we are just going to place these pads. So you can see down here, we have coordinate points of everything. So these are your X and Y's. And then the DX, you can hit space and it'll zero out everything. So if I just want to make sure, I could just zero them out to be the same thing, but you can always have a nice reference point. So I'm just going to put this one directly at the center there. And then from looking at this chart, we know that these should all be spaced 5 apart. So what I can do is just select this pad and I can just duplicate it, place it in the same thing, and then select that one. And we can do positioning tools, move exactly. And I can just say -5, and then that'll place that there. I can do the same thing again. We can duplicate it or hit Command D, place it, and then position tools. And this time we want to put it at 5. So now they're spaced, but obviously they all say 1, and we haven't actually looked at the holes yet. These reference things, you'll see they just show up and say certain little values that we can set and everything. But we need these numbers here to match the actual numbers in our schematic. So if we go down here, we can see there's this 1, 2, and 3. And so this is our way for our footprint to connect up to our symbols to make sure that the right pins are connected. So it's very, very important that you get this right. Sometimes they won't be numbers, they'll be letters like this S and T. So if you had a footprint that did not have S and T, but the symbol did, that'll cause some issues, which we might run into later. So we just know that we want the 1 to be the one that goes to the 3v3 and the 3 to be the ground. That doesn't matter too much because we just know that the center one we need to be 2. So we can say 2 here, and then we can say 3 there. Where this does matter though is when it comes to sizing. A lot of times you'll see ground pins are square or rectangular pads instead of these circles. So that can be a nice thing to add. So here we can just come into 3 and make this rectangular. So now it looks like that. And then we can go through and we need to make sure that it is a 1.2 diameter. So you'll see 2 different values here. There's the hole shape and then the pad shape. The hole shape is that actual kind of inner diameter of the drilled out one. So that's what we want to make 1.2. And the pad shape is going to be after this outer diameter. So you can take this pad shape minus the hole shape diameter, and that'll give you just the length of this right here. Take that divided by 2, and that'll be each one of these. And typically I like to just add pretty much a millimeter on top of that. So here we can make it 2 by 2 or 2.2. That's being pretty generous. You could even throw that to 2. So this will just be the amount of space on each pad that we have to solder. So this will work totally fine. You don't want this too thin, and then you don't really need it too big. If something is like this pot where we're mounting it, then bigger can be better. So we just get a really secure solder joint on there. But yeah, that should be good for that. And then we just want to do the same. I guess you probably should have done this before duplicating it, but this works fine. So then come in here, and then the same thing with the X and Y will just set to the same values. So it is a square. And that's really it for this. So this will work totally fine. But we can do a few more things. One is that we want to give some sort of indication on the PCB that these are one component. So one way we can do that is with this silkscreen layer. As I'll explain later, the silkscreen is where we can put graphics and things like you can see on this PCB. Basically everything that isn't the pads, like this white circle there and my name down there, that's all on the silkscreen layer. So we just want to sort of put a little rectangle to group these things. It really doesn't matter a whole bunch. So I can just do that, and that's probably good. You could have it be nicer if you can do a Command-Shift-M or hit this measurement tool down there to kind of measure the distance between things. So if you want to get them exact, you can totally do that. But another thing to add is this courtyard. A courtyard layer, basically, it doesn't print anything, but it will make it so that your parts can't overlap when the courtyards are touching. So if I put a courtyard to be pretty much the exact same thing as this one, then that means, here, let me put that down. So that means that something couldn't be placed to overlap with these two courtyards. So say I had two of these pots, obviously the pads couldn't be directly overlapping, but now there's this extra little leeway space, which is probably good to put with the actual pot, the circle itself, which is something else we can put. So here, as you can see, we have that 16 millimeters between the center of the pot and the pins. And so it would be nice to kind of just show a little indication in the software of which way this pot is oriented. And it can be a little strange to think about as first we can select our silkscreen. But if you'll remember the PCB I showed you earlier, we have all the stuff soldered on one side, and then the pots are actually the opposite side of that. So like with this PCB here, let me switch the screen. With this PCB here, everything is soldered on this top. So this is actually the front, or that F layer, as you can see in here, and then this is the bottom layer. But the thing is, you can solder on either side with these through-hole components. So this is just a random PCB. This is the one that we're actually making. But I made this and all the other ones so that the pots are below like this, which means that if this is the front, that the pot is actually on top of these pins right here. It's kind of confusing to think about, but basically we just want to make sure that we place this diameter circle above these pins. So as we can see, this says 16.5 diameter. There is this one that says 17 over here. We can just go with this 16.5. So if I want to select this circle tool, make sure I have the front silkscreen layer selected, and I'll do that same little thing where we can create this in the center. I'll set it to any radius for now. If you just click and then go back to this tool or hit escape, and then I can hit E on the circle and then select our radius. So we went half of the 16.5, so that would be 8.25. Select that, and then we can do the same move exactly. In this case, we want to go up, which is actually negative Y, so I can do negative 16, and it places it right above it. So that's pretty much everything we need. You could add the courtyard so it extends out, but the thing with that is, well, two pots couldn't be next to each other that close because of this whole pot size. Other parts could totally fine sit there, so this is something that I would just pay attention to, and that's why we make this whole graphic, is so that if you were to put two pots way too close to each other, and with the drill tool it was totally fine, and then with the pins it's totally fine, but now we would be able to see those overlap, and we know that we should not put them that way. But besides that, this totally works great. So I can hit save. We could maybe just put potentiometer in front of this and then put an underscore, because that has how they name their own. And you could make your own library, or you could just add it to their potentiometer underscore THT. So there we go, and I can just hit OK. So now coming back into the schematic, we just want to hit our assign schematic tool, select potentiometer. We want to find the library for it right there. Probably scroll down, here it is, RV16A F, and now I can just select that for all three of those, hit apply, and we are done. So it's pretty simple for this circuit, but obviously you can maybe imagine that that part can get very complex because you need to really cross-check all your parts, all your dimensions, but for us, it was pretty simple, and now we can move on to the PCB. So how do we make a PCB? Well, to start, we want to hit this little green button in here. This will switch to the PCB editor. Similar screen, but overall very different tools for us to use. And before we get into any of this, there's just some settings that we want to change. So we can go to File, Board Setup, and now we see here, these are all of our layers, like literally the layers that will be on the physical PCB, and we don't need a lot of these. So all of these user ones, we're just going to totally uncheck because they clutter up so much and we won't be using them at all. Many of these other ones we will not be using, but I wouldn't just turn them off because they are things that you might use someday, but a lot of them are just for more professional factory settings and things. Some of them that KiCad's already doing some stuff, but really what we're going to be using is the FCU and the BCU. This stands for the front copper layer and the bottom copper layers. So that's where all of our actual routing will be done. And then we have our silk screen, which we use. So this is your front silk screen and then bottom. So if you want to put some graphics on the bottom, you can do that, or the front, you can do that. You'll see all these footprints have all those base shapes and stuff like the one that we made. And then we have the courtyard. That is one for sort of the testing, as it says here. So that's how we make sure we don't place things too close. And then another layer we'll do things starting off is this edge cuts, which is basically where we just define the shape of our PCB itself. So that should be good. We just turn off these user ones, so that'll just free up some of the clutter over here. The next thing that we can go to is this constraints here. I think some of these minimum clearances being 0 isn't the best. So I like to set these to 0.15. This doesn't change a whole bunch, but it'll just sort of put these constraints in so that if we break these own rules that we set, then the software will yell at us. And since it was originally set to 0, that means you could have distances between your actual connections be infinitely low, you know? So it's good to set us some guardrails there. The rest of them should be pretty much fine. Then we are going to come down to net classes, because if you remember, these are those groupings that we made earlier. So we made our special power one. So what we're going to do here is just make the track width of the power one 1 millimeter. That's because, as I said, the power, especially the DC jack that we're going to plug in, is pulling way more current. So we want to make sure that's a higher track width. There is an actual formula to calculate the track width that you're supposed to have, or like the minimum track width that you're supposed to have. For the sake of the Daisy and all of this, I promise you these will be fine, but in the future, if you're to really get into this, that is something you will need to calculate, just because if a track width is too small for a certain current, that would be very bad. So you don't want to do that. We can honestly come in here and make this 0.25. We have so much board space, so it really isn't going to hurt us in this case. But there's other times where you might have like your track width actually be sort of changing based on where it is, but we have a pretty big board for not a lot of stuff going on, so it really doesn't matter. So we can just hit OK on that. So the next thing to talk about is just our grid sizing. You'll see all these different ones that are kind of feel random at first, but you'll see they're always referring to these inches. That's because a lot of the ways that these factories and these machines works are in the measurement mils, which is 1,000th of an inch, so 0.001 inches, as you can see here. So like 1 mil is 0.025 millimeters. We will be using this user grid typically because this is the average spacing that PCBs use, which is 10 mils. You can see with the 0.01. But to start, we want to define our board size. So for now, I'm going to set this to 1 millimeters since our Tata drill tool and everything we've done so far has been in millimeters. So yeah, we need to use this rectangle tool. And then as I mentioned a little bit earlier, edge cuts is going to be our like layer that we get to define our board size. But we need to figure out what we want. So if I pull back up our little drill tool here, we need to make sure that we make a PCB big enough that it can fit these two pots, but small enough that it can actually fit in the enclosure. So the first good way to check that would be to just search the Daisy Seed dimensions. So if you search it, there should be a little photo that we saw earlier, 51 millimeters. So we know that Daisy will be going here. So that's 51 millimeters. So we know we need at least that. And then we can calculate the distance between these two pots. So I like to just touch and then you can see which one each is. So we know that's the left one, meaning this would be the right one. and we can just see the distances between these two. If you can remember, the middle is 0, so this is -20 from there. So basically we can just add the absolute values of these. So that's about 40. So we pretty much want to go by this DaisySP dimensions, and we want to give it a little extra space because there will be some connections going between the sides of that. So I say we could just round that up and throw it to 60. So we know that the width is going to be 60, and now we need to calculate the height. So again, we can look at this. We know that this LED, we're going to actually put in the PCB like centered with it so that we can just wire it directly into the PCB. And then we also know that wherever this drill is, 16 millimeters below it is where our actual pins are. So meaning that the PCB probably will not actually be touching up here. So we can take this Y position, which is 38.1. Let's minus 16. And then we want to add wherever this LED is, because that is somewhere probably less than 0. So that's this 5.2, -14. So we can just plus 14 to that, and that is 36 millimeters. So I'm going to just do pretty much what we did last time, which was add about 10 millimeters to that. So we can make that 46 millimeters. It's probably more than enough space. You could have it less, but for the sake of this, adding like a few millimeters to your PCB is not going to increase the price at all. So I would just give yourself a little bit more and make sure it still fits. You could also go and Google the enclosure dimensions, but we know that these drill things line in here perfectly, so we should be totally set with that. So we want the 60 by 46, right? Yes, 46. So if we come in here, make sure edge cuts is selected, select your rectangular tool, make sure you're on the 1 millimeter grid, and then I can do this and it'll just nicely tell me. So there's 60, and then we wanted 46, and boop. So now we are good on our actual board layout. There are other things you could do, like as I mentioned before, the corners of these enclosures have these little screw things. So say you wanted your jacks to be actually mounted on the PCB, and maybe you wanted them to be mounted at the top, so you needed that to press up against it, which I do have a build that I'll show you that I did that. You could use something like the line tool, so you can draw these straight lines. I think you can hit shift space, and now it'll lock it with 45-degree angles, so I can say draw like a cutout or something. And as long as you don't have any actual gaps within your PCB, this will be totally fine when you submit it to PCBWay. So you can totally do that if you want some odd shape. But for us, this is going to sit just pretty much directly in the center of the pedal, so a rectangle will be perfect. So next thing we want to do is actually bring in all of those footprints that we set earlier, which we can nicely do by just hitting this button. So I can hit that and then hit update. And we have some warnings here. We'll ignore those for now. Just hit OK, and then boom. So there are all of our parts just nicely set out. We can see our nice footprint that we made earlier, and then all of these different jacks and the Daisy itself. So let's see again what that warning is telling us. So it's saying no net found for component J2 pad 1, no pin 1 in symbol, and then the same thing for the other one. So this is exactly what I was talking about earlier, when you have a footprint that doesn't have the correct pin numbers or letters. So our jacks have this S and T, while our pins here, our pads, have 1 and 2. So if I just take out these two footprints, and we need to tell it what the actual correct things are here. So if you remember, we have our tip and our sleeve for the audio jacks here, and the sleeve is ground. So we want this pin 1, which is the one with that sort of rectangle. So typically that's an indication of ground. We want this one to actually be S. So I can set that there, and then we want this one to be T. And we can do that same exact thing here. So now hopefully when we do this again, it'll tell us we're totally fine, which it did. So now we have 0 warnings, 0 errors, and we are totally good. You'll also notice all of these blue lines. So this is just our wires. All of those wires that we set here, it is just nicely telling us which ones we need to connect. So like we see this ground goes to that ground. It also says them in the pads here. So this pot 1, if you remember, that was our connection name, and it comes all the way down to this pot 1. So it's just telling us what we have to connect them to, which is handy. But the next thing that we need to do is actually place these exactly as our schematic is, our drill schematic is. And we can pretty much do this the same way we made that footprint, which is using that move exactly little tool. So we can just place 1 and then move everything according to that 1 right there. So first I'm going to get these out of the way and just place one of our first jacks at the top left, because we pretty much know it's going to be there. We can always move these later, But yeah, we just need that starting point. And as you can see, this top circle is out of the PCB, which is exactly what we want. That is totally fine and how it should be. So now we've placed that one pot, and I like to just do the thing where I just basically overlap one. I can put them over that and then right click, and then it'll ask which one you want to select. So I'll select that footprint, and I can go to positioning tools, move exactly, make sure we reset that. And then we want to see here, we have this top left one we know is this. We want to move that over by here by these combined absolute values. So we have that 20.3 plus 20.32, which is 40.62. So we can just put that right in here, hit OK, and now those are spaced perfect. So I can do that same thing. I'm going to place this one over there, go in, make sure we select RV3, go to positioning tools, move exactly. We're going to reset that. And then if we get this up, now we need to do two moves. We need to move by the X and the Y. So here, let's just do the Y first. We have this one is at 38.1, and then this one is at 12.7. So we can do 38.1 minus 12.7, which is 25.4. So let's copy that. So we're going to say 25.4, and then we need to do the X. So we can see this is negative 20.3. So we just want 20.3 to be able to move it to the right, and then hit OK. And there it is, perfectly spaced. So there's all of our pots. And now we basically know that all of these in reference to each other are completely right, meaning that we can move these any way and they will be fine. I guess I selected the edge cuts there too. One thing you can do is I can go here, hit it, and then over here we can say locked. So now you are not able to select this at all unless you were to go down here and in the selection filter you can check that locked. But we don't really want to be able to move this around or select it at all. So I can just do that right there. So now, like I said, we can get this so it's spaced evenly. Again, this isn't totally needed, but I like it to be symmetrical. So we can select this measurement tool or do Command Shift M. And then let's just see what the entire width of this is. So we have 53.620. Also for this measurement tool, they have a couple nice things about it. You'll see, like if I were to measure the distance from here to there, or I am in that locked mode. So I can measure from here to there and it will tell me the length of the line, but it will also just tell me the total distance of the like X or Y. So if you look at that Y value, if I keep moving this and if I were to be able to move it straight, you'll see that the Y stays the same because that's the difference of this going down to here, which is really handy to do. So I can just see the difference between these, and then I could go and cross-check that with the drill schematic. So this isn't just telling you the length of this line, it will actually just tell you the difference in Y. Handy thing, but for now we just want to try and space these evenly. So I can see that that is 53.62 millimeters. So if I were to just take the total width of this, which is 60, minus 53.62, then we have 6.38, and then we would want that divided by 2, so that's 3.19. So we want the distances between this side and the actual board to be 3.19. It's probably not going to be exact. It never really is with the floating point stuff, so it doesn't really matter. But let's see, this is 2.6, so we want that 3.19 minus 2.6, and that is 0.59, meaning we just need to move all of these over 0.59. Hopefully that made sense, just kind of simple arithmetic. But I can go select all of these, right click positioning tools, and then 0.59, hit OK, and then let's see if they are reasonably equal. So that's 3.19, and this one is 3.19. So now it is symmetrical down the center. So the only thing left that we need spaced appropriately is the LED. So we see here we have this knob, which we have placed, but what we've placed is the pins that are 16 millimeters below that. So we need to just find out the distance between these two and then minus that 16 millimeters. So here is my LED, which is at -14, and then this one is at 12.7. So those are the differences to them if we just add those together. So they are 26.7 millimeters apart. And then if I take all that and minus 16, it is 10.7. So now I could try and do that same thing where I just place the LED over top of it. It's not going to be exact anymore because of the grids, but that's all right. Instead, I can just sort of place it down here, and now we can use our measurement tools to try and get everything exact. So we see here that this is not perfect. We are not lined up perfectly symmetrical with the center of this. Typically the measurement tool, you're able to latch on to the center of things, which is nice. So I'm at the center of the LED there, and then the center of that pad there. And you can see we are over 0.16 millimeters to the left. So we need to throw this 0.16 to the right. So let's do that, 0.16. There we go. So now hopefully if I measure the center here to there, yeah, we can see we're at a 90-degree angle now, and we are 12.6. So if we just take that 12.6 minus the 10.7, I think that would be 1.9, and we can just move that up. Exactly 1.9. But as we found earlier, moving up is actually negative. So if I hit that, now if we measure, we are 10.7 millimeters. And now since we have the center of this here, I can click that and check this. So that is going to hopefully be this value, 26.7, and we are good. So now we know that our knobs and LED are perfectly spaced, and the rest we can kind of just place so they fit nicely. And there's still a couple guidelines that we want to follow here. Typically, if you have complex or like a lot of parts, this is sort of the bulk of everything, is where you place things. That is like the most important thing, because the whole thing is trying to eliminate how long your tracks are. Tracks are what those connections are. So like you can think of your wires, they are now called tracks. So up here you can see this is where we can add our tracks, route tracks, and we will get to that soon. But first we got to place everything. And even though we don't have many things going on, there still are better and worse ways to place them. So even when placing our Daisy, we still just want to think about this a little bit. So here I have my pinout, and you can hopefully tell with this footprint that this is where your micro SD is. You could also just zoom in and see all of the numbers and everything there. And we want to just see where all of this ADC is and make sure that we place that on the side, probably with the most pots, because we have 2 up here. And like I said, we want our tracks to be as short as they can be. And so if our ADC was like all the way down here, then that's just going to add all of this extra length and having to cross through all of these holes or go around it. So we just want to try and have the ADC up here. So hopefully maybe just this one will have to be a little bit longer. And then we know that the LED and the foot switch and everything are just going to be these digital pins, which there are so many on either side, so it doesn't really matter as much. So we can see all of these ADC pins are on this right side of things, which is right here. So all below here, and we can even see the pots that we've already connected, which we will be changing. But I can just come in here and hit R on that so we can rotate that way, and that should be totally good to place. Another thing I'm going to do actually is switch this over to the user grid, because as you saw with the 1 millimeter, we have a sort of pretty large gap between being able to place stuff. And if I go to the user grid, now I'm able to place them much more freely. So we don't have to perfectly get this symmetrical or anything. I'm just going to place it like that, and that should work great. And now we can place something like the foot switch, which is going to be wired on. And if you kind of can just picture it, that foot switch is below everything. So we can pretty much just place that as close to the bottom as you want. You know, give it some space. It doesn't really matter. The foot switch, it doesn't have to be like as close, because we can just make one of these pins up here the actual pin for the foot switch, which is short enough and there's nothing blocking it. The resistor goes next to the LED, so we should just place it right next to the LED. So I'm going to do that. And you can see here we have, this is the LED pin that's going to go into the Daisy, which again will probably change to one of these 8s or 9s if possible. And then we have this one, which it shows our little blue line is going to connect to this. So we might as well even short the distance to this, so I can rotate this a bit, and now we're here, and then we can rotate this LED. But you'll see if I rotate it, it kind of does it somewhat annoyingly. And honestly, instead of having to deal with rotating it and then moving it, I'm just literally going to switch these around. So I can put the foot switch over there and the LED here, and then re-rotate that, place it right next to it. So now we've just shortened the distance a little bit. We'll be able to connect those right up, and then the foot switch doesn't really make any difference. We can have that go up to something there. I can probably rotate this again just so those grounds are next to each other, and now this one can connect to the 5 or the 6 or something. Another thing I'm going to do just before we forget is I'm going to select these pots and the LED, and I'm just going to lock these because we have set their position. We don't want to accidentally move them, and it could just screw up everything if you accidentally move it and then you still order it because you didn't realize. Even if it's over 2 millimeters, that could totally screw up how they fit into the enclosure. So we're going to lock them, and it's going to give this big annoying purple thing, which we could probably turn off somehow, but it's fine. So next we want to place this DC jack, which we can see this line from here is going into this. So we know that that is that V in as it says. So we want to place that close. And we also know that the jack is going to be soldered in up top here with wires. So we might as well have it on that side too. And that's a pretty short distance, so that should be fine. Sometimes I'll probably do this with the auto jacks. I literally place it under the Daisy just because it makes that path incredibly short and it doesn't really add much complexity if you use, we're just soldering on wires here. So it's not that big a deal, but I don't know, I'll probably just place this one up here. And then the jacks we can see that the lines are coming in here, and you can see this one that keeps jumping around. That's just ground. And as you know, like so many of our parts have ground. So it's constantly just going to connect that to the nearest ground. And you'll see soon that we're going to do a special thing for ground. But for now, I can just kind of put that one above that. And then we need this one. See how I accidentally moved the Daisy there? So if that was your pot, that could be annoying. Even the Daisy we could lock, but I'm just gonna not for now. So we want this one to also be there. So we can probably, oh yeah, I keep selecting that Daisy. I'm actually going to lock that. So we're gonna lock and it's gonna be all purple and weird. So I'm gonna rotate this guy so we can have that one just over there and then this over that, because why not? So now we've pretty much placed all of our things. There's just a few steps left before we actually start routing. Mainly, we need to change where these are all headed. So this is what I was saying earlier, is that we are also, make sure you save, I haven't saved. But we want to just route these to the nearest thing. So here we want all of these pots to just be to their closest ADC. Because like here we see that we just stacked them here, which is totally good. It seems pot 2 we can probably just keep there, but now pot 1 would have to cross under pot 2, and then this pot 3 would have to come all the way around, and then it would be a hassle. No matter what, pot 3 here is not gonna have the best time, but it'll probably be fine. So we just want this pot 1 to have something close to there. So let's pull up our chart. In these high 30s, we can see 35 is our highest, so that's probably where we just want to throw this. So we can put the 35 there, which is going to cause some problems with these crossing. There are ways around that, but I'm honestly just going to move it down. I think it's really fine. Again, this is probably fine practice in the context of this, since we only have these 3, but if there was even 1 or 2 more, then that's a lot of wires that are coming out from this Daisy, which they are lifted up a pretty good amount with these like headers you can see. So that's about the space of there, these black little parts here. So there's all that space under there for wires to come out. But if you were to have much more than this, now you're going to maybe be pinching wires when you close it on, which could be bad. But yeah, there's not much going on in here at all. So I feel pretty confident just putting them under the Daisy. But yeah, we want this pot to go to 35. And then this pot is probably totally good there. And then the closest one here is most likely going to be one of those just center ones. So we can just look at what is above there. So like around the 30, and we can see that those are totally fine. So that's like ADC 8 and 7. So just remember that pot 1, 35, pot 2 is good, and pot 3, let's put to 30. So we can come back here and then we can just rearrange this. So pot 1, I want to put to 35. We will have to delete that X, so I can delete the X. Pot 2 is good, and then pot 3 we want at 30, so I can delete that X there, place that there, and now I need to put those X's back, so I can hit Q and then put 2 X's. And before saving and bringing in all those changes, let's go down here and do the same thing. So we can see this foot switch is close to 5 or 6, so let's check, are those good? Yep, so we can put it to either. I guess 6 is better. And then the LED here where this resistor connects, we want to see. So those are our audio pins. So let's see if maybe 15 is good. It is. So we can put the LED to 15 and the foot switch to 6. And make sure to put your X's back. So then I'm going to hit save. I'm going to just hit the checker in the circuit so we can know if we, yep. So it is saying that I have left all of these X's here. I have no idea how I ended up doing that. But it's good to just check these things, because obviously this doesn't really matter, but there could be things that do. Let me check that again. We're all good. And now we can come back in here and we want to just do this again. So I can hit update PCB, and now it is rerouted. So we see pot 1 goes to that, and pot 2 should be the same. and pot 3 is now here, and then all the other ones. So now all of our wiring should be totally good. Make sure to hit save on both your circuit and PCB, and now we can start to put down our tracks. So first thing to know is what our 2 layers are. So the base sort of default PCB you can make are just these 2 layers. You'll see a lot of pedals might be 4, like that Terrarium PCB is 4. That's just so you can have less sort of interference and just much easier time routing, because you'll see that when these get complex, they are just these little puzzles. They're very fun, but it can be a lot. So we have our front copper layer and our bottom copper layer, and these are just completely separate routings that we can do. Like here, if I were to go on my front copper layer and then select this tool, which you'll see is X. So I can hit X, and now I am routing, and it'll have this sort of auto routing thing where it'll try and make your sort of range around. I wouldn't always trust it, but it can be fine. So say I were to place that there, and then we can see this 3v3 is over here. So now if I were to go place it, and we can already see that this 1 millimeter is so much bigger, so that's good because this holds power. So like in this case, I can't actually cross over this wire here. I would have to go completely around it because those are on the exact same layer. And so if those were to cross, then they would connect these 2, which would then totally short our potentiometer. But if I were to go to this bottom layer and click that, now I am able to go over to that because these are 2 separate layers. But that doesn't mean that for something like this, I am going to just perfectly start crossing everything, because this can create some issues. Now, this is where I definitely have some gaps in my knowledge because, like I said, I'm not an electrical engineer and I am not a professional PCB designer. It is a skill that I am learning, but I have hundreds of hours to go before I can accurately come on here and tell you advice about that. So what we're going to do is make what's called a ground plane a bit later. We're going to do that after we route everything, which is basically where we can dedicate this entire bottom copper layer to just being ground. And since we're going to dedicate that to being ground, it means that we don't want to start throwing all of this other stuff there, especially with dealing with something like these jacks. I'm not going to throw this here and then have this be a ground layer, because that can create some problems with mainly noise and all the voltage stuff, because we have no regulators. So all of the voltage coming from this might be a little bit like out of control and unpredictable. So we're not going to mess with that. So we want as much to be just on this front copper layer as we can without ground. And sometimes we might have to go over into that bottom layer, which for things like your pot, that can be totally fine, because this is honestly not that important, but it's also not one of the main things like our audio inputs and outputs and our DC jack. So all of our sort of ADC stuff we can not be as careful about, but the rest of it we want to make sure we are good. So that's why I sort of place those within the seed itself. But in the case of these, I would just start with all of your important things and then we can do the rest from there. So I am going to delete this. You can press U to just select the whole wire, because if you were to click, it will only click a section. So I could always just click and then hit U and then hit delete. But yeah, I'm going to just connect all of these simple things here. So I will press X and then connect that. We will connect our audio here, audio there. I'll connect this resistor there. And then we'll come and do all of these 3v3s, which unfortunately have a pretty big distance to cover, which is fine. So you see the auto thing put these like pretty close. So that's something I would be maybe a little bit cautious about, but I think it should be fine in this, because they also do put this clearance that we had set. So as long as it's not over that, then we should be good. So we want that, and then we want that short distance there. So that should be good. And now we unfortunately need this one to sort of cross all the way over. So again, like I don't like how it's having this overlap so much. So I might even have this come out just a little bit more so I can click there. So now that's locked. And then let's see what it's doing. So that should be good. And now you'll see those blue lines disappear once those are connected. So we know that all those 3 knobs are connected to our 3v3. You'll see that has created some problems for things like our foot switch, which we can deal with in a sec. But yeah, okay, so next we want to just connect all of our pots. So ones like here, I'm just going to go and select that. That looks great. We're going to get this LED. That looks fine. And then we see we have these ones that cross. And for now, I would say that something like this is a short distance. This would be totally fine to just use that bottom layer. And then here, this one, we can just wire right through here since our track width is pretty small. And then same one with this, I could also just do a blue. There are also these things called vias that I'll show. So if I wanted to just use this and then I can come over here if I hit escape and then use this via. So I can basically transfer this trace onto another layer. So now I can come select this bottom layer, go there, and then I could even put another via and then go back here. And so now if this was like a really important sort of thing, then we're minimizing the amount of space that we are on the other layer. For this case, it really wouldn't matter. It's just a foot switch. So just for simplicity, I'm going to keep it all on here. As far as I know, that doesn't make a big difference with the foot switch, but maybe it does. I'm not totally sure. So now we have some last remaining lines, but as you can see, those should all just be ground. So let's look, and yeah, I think we are all set with everything except the ground. So now this is where we can make a ground plane, which we do by making these zones. Zones aren't specific to ground planes, but there are how people do it. So we can basically just dedicate this entire bottom copper layer to just be ground. So it has all this space and we don't have to worry about really routing stuff. There are ways that you could like block off a section and have to do it, which we can check to see. But for now, we're going to go to this add filled zone, and now we have to place these little things. I'm going to set our grid back to 1 millimeter just so we can have it right on the dot. So now we click it and it will have us select the layer. So we want the bottom copper and we want our ground connection. So now that first line has been placed and it's coming out, and then I can place the second thing there. And now we can see it is starting to show us what our zone is. Then I can come down, hit that corner, and then come down, hit this one, and then come up, and you have to connect it to that first point you set. And then there we go. So now that ground plane is sort of set, or that zone is set. And now I can just hit B and it will fill that zone. So now we should see this big blue zone. And then if you are to look, we can see, like if I were to select that bottom layer, we can see where it's not filling the zone. So all these gaps between the pads, because obviously we don't want these to be ground. This isn't ground, so those aren't touching. This track right here isn't, but then all of these are being connected to it, as we can see from the little bridges there. And we can also see that all of those little connection wire things are totally gone. So our PCB is pretty much done. I'm going to hit save. But there's a few more ways that we can just check and make sure everything is good. So just like there was that ERC little checker thing with the circuit, we have the DRC, the design rules checklist, that I can hit. Let's hit run DRC, and we can see we have 0 errors, but we do have all of these warnings. So let's see what these are saying. It is saying footprint does not match copy and library connector wire, which is because we had went in and changed these. So instead of these saying 1 and 2, we made it say S and T, and that's yelling at us saying like, hey, your footprint doesn't matter. So it's just giving us a warning, which is good to know. But in our case, we don't really care. We did that very purposely. Now this is saying silkscreen is clipped by our solder mask. So let's see, that's talking about this right here. This is another thing that doesn't really matter. Same with silkscreen overlap. So it's telling us we have all these points, and it's good to know. And there can be reasons why this matter, but it really doesn't for our case. We do not care that these are overlapping. It is not going to create any issues. So we really don't have to worry about it. It's pretty much just warning you that when you submit this and get it ordered, things over here might not look exactly like they do here, because obviously like this silk screen is not going to go over the pad there. So it's just a little warning to let you know that, and same with like some of your wiring and stuff, that everything will not look exactly like what it says here. So now the PCB is by all ways totally done, but there is one more thing that I think is smart to do just so we can check and make sure that everything is correct. And that is the 3D model. So I can go here and go view 3D viewer, and you can see that we have our LED, we have the Daisy, we have a resistor, but we obviously do not have any of our pots. And that's because it doesn't know what model it is, because we found this online and this is our own part and we made our own footprint. So obviously it won't know. And this is something that we can pretty easily typically find models online. Footprints not as much, because obviously this footprint was really easy to make, but models you can totally find, just like this Daisy one that is already here. And why might you want to do this? Well, I'll show you how we can take this 3D model and put it in a 3D modeling software to compare it with our enclosure and even all the drill schematics if you want to just triple check that your work is correct. I think this is super helpful to do because like when I started off, like I said, there was so many iterations on these PCBs by just sometimes the sizing, which is like not what should happen. The sizing should be the thing that you just have down because it's pretty simple math and it's just like it should line up perfectly. And there was times like I remember the first time when I had the screw holes not line up because I had PCB mounted jacks and just all of these issues that you don't think of until they happen. So I think it's a really smart idea to get into the habit of triple checking everything, because every time you order parts, that is money that's costing you. That's all this waste you're producing, labor you're paying for that's going to waste. So the less amount of that we can do, the better. So I'm going to go and search for this pot. So that was the RV16AF, and I'm going to just search for 3D model. And I have done this, so I know that there are plenty. So we can see there are all these different websites, like we have this grab cab. So let's see. Yep, we have the exact pot that I'm using. This is the alpha. This is literally the exact one I had ordered. This one has a slightly different shaft than mine. As you can see, this has that totally smooth one, and that shouldn't really matter because that won't really make a difference with this overall rest of the spacing there. So this would be totally fine. We could download that. I already have these downloaded, so I'm not going to download it right now, but we can also see SnapMagic. Let's see 3D model. And yep, there we have pretty much the same thing. So that will also probably work perfectly. So once you've downloaded your model, you can come to, there's a lot of different places you can put the model. I'm just going to go to my documents, then KiCad, and then this is the version I'm using. And then you could put it in 3D models, which is where I did, or third party. And then once you've done that, you can come in and select your objects. So here we'll have to make sure that locked items is checked, because we will have to select these pots. And then you can come to 3D model, and then we can hit add here, and then the folder, and then just go to that folder that you found. There are paths you can configure to make sure you have this at 1, but this also works. So then I can just select this right here, and now that pot is going to appear, and now we just have to position that as best as we can. First thing we want to look at is what the actual orientation is, and we can see that by this footprint being on the top. And as we know, the knob is going to actually be on the bottom. So we probably want to rotate that way. And now that's pointing the right direction, but we need to rotate this Z over a bunch. And so now we just want to offset probably the Y, so we can just click that up a ton of times. And this doesn't have to be perfect. So this is interesting. So it is not totally lining up, because as you can see, this diameter in this circle is perfect, while these pins are not. So this could be something to be concerned about. I'm not sure what exactly it is. I wonder if it is that whole 0.5. I'm not really sure. So it could be the model, it could be our thing, but I know that it actually isn't a huge deal for this sake. One, because it's not that big a difference, but also all of our things have like that level of sort of clearance and tolerance that we're able to give it. So this is not going to ruin our design, but either way, I can move that down. So there we go. We want to make sure that these are correct, because obviously the pins will not be able to move past that. So that should be good there. And now I can hit OK. I'm sure there's a way to just link a footprint to a 3D model or something, but for now I'm going to just kind of redo that for everything, and just I can look at these values or write them down or something, and then just go apply that to all of your pots. All right, so now I have set all of those. So let's go back to our 3D viewer. And now we can see all of our pots are there. So you might be a bit concerned because the daisy is totally poking there, but the daisy will have those headers. That is something that in the 3D model we can add. But yeah, these pins will not be poking through all the way there, so do not worry about that. And the LED will be totally on the other side. So that is maybe something that we could go in and edit. I might have this just come a little bit above it. We could like measure that out, but I'm not too worried as long as like you see that it is in the right sort of space when we compare it with the drill, then that's all that matters. So I'm not going to totally go over like Fusion 360 and throwing this in there to really test it, but there honestly are some simple ways that you can test it yourself. Just like a slight fail safe one is that I could come here and kind of straighten this out and just take an actual screenshot of this. And now I've placed the one photo, and I'm going to place this one on top of it, and then just have the opacity be a lot lower, say around there. And now we can just sort of look for the holes, and we can already just see that like, yeah, that lines up. I mean, obviously that the PCB is not a perfect top down because of the angle, but this is all I mean is like, just make sure that if this LED was like up here, that you just forgot, maybe you forgot to minus the 16 or something, but this is totally fine, and we can scale it or scale it down to make it, try and match it better. But I can pretty much see from this that like, yeah, that'll work. Another really smart way is that we can go here to print and then hit print again. and I can go to hit PDF. That was with the silkscreen and edge cut layers selected because we don't really need the routing. So then I could actually print this out and set all of my parts just on there. So this is another way that is less about the actual drill, but making sure that if you maybe made a ton of footprints that each one fits correctly. This is a great way to check footprints. Check spacing. This is a way that I could, if I had an enclosure lying around that was the correct size, I could just make sure everything loosely fitted. You could even like cut some holes in it. I don't know. There's also a time where I had like 3D printed out PCBs because I needed to check sizing. All this to say, triple check your work. Make sure that you don't have to order stuff a ton of times because that shipping will definitely add up. But once you've done that and you're sure things are right to the best of your knowledge, then we are ready to submit this to PCBWay and get them ordered. So the main way to submit your PCB is with what are called Gerber files. So we can come up here to File, and instead of Export, this is where we could do export our 3D model and stuff, but we're going to come to Fabrication Outputs and hit Gerbers. And then all the default stuff should be totally fine for this PCB here. We want all of these selected. That's great. And now I'm just going to choose the output directory. You could just make this in the actual one itself. So I'll just put the Gerbers right in there. I'll select, maybe make a new folder. I forget if it does by default, but I'll hit open. Do you want to use a plot? Just say yes. And then I can hit plot. And then we actually need to hit generate drill files. This will just tell them where to obviously drill all of these holes. So then hit that. And that is good on your Gerbers. So now we go exactly to where it spit those out. So here I have the Gerbers folder. It seems it was good that we made it a folder. And what we're going to do is just zip this. So I'm going to say compress. And then we are going to go onto PCBWay. So I know PCBWay might have sponsored this course, but I had actually prepped this whole thing and even ordered my PCBWay on PCBWay before they ever reached out to me at all. So I have been using them for years. It is cheap, it is quick, and I've never had an issue. Their customer service is great. And yeah, this is what I've been using. And there are other options, but I've never had an issue with PCBWay. They have all this other stuff that I'm sure I have mentioned before, but yeah, they have a nice way for us to get an instant quote by just putting in our dimensions. So our length was 46 by 60. I'll just select 5, and then ours was a 2-layer board, and the 1.6 thickness works totally great. So I can hit calculate, and now it'll tell us our price. So yours might be by default a lot more because of DHL or something. These are all your different shipping things, at least if you're in the US like I am. I always just select the cheapest. I've never had a package lost. I've never had anything damaged before. If you're more cautious about that, then feel free to select something more expensive, but obviously the shipping cost is the main cost here because your actual PCB is only $5. So it's up to you. I mean, for something that's $5, I feel like spending $20 on shipping is maybe not worth it. But if you were to get everything like pre-soldered or something, then it could be worth paying for a better shipping company. But luckily for us, we can leave everything here just to the defaults. I could go over what they mean, but I either don't know it or it's just not needed at all for this. So they do have this beta where you can upload a Gerber file for them to just more helpfully calculate the price for things. Our PCB is so small that it doesn't really matter. So we can just hit add to cart, say agree, and then you're gonna need to sign in. So now this is where we add our Gerber file. So just select that .zip. There we go. So I can hit submit the file now. So your actual PCB will need to be approved by them first. So if you either do all these things wrong or maybe selected wrong values and you actually have a higher price, then they will tell you that. So you do have to get it approved. In something like this that we just made, it'll probably get reviewed very shortly. And then once it does, you can go pay for it and get it ordered. So we have our PCB, the code, our drill schematic done. The only thing left we really have is the actual graphic for the pedal, which luckily is actually pretty fun to do. But there are some little quirks about ordering the UV printing service on Tata Electronics. So I'm just gonna kind of go through those. They have a nice documentation on it. Not really, they have a write-up, like a page just kind of saying what you have to do. I'm not gonna like teach you how to use Illustrator in this. I barely really know the intricacies of it, but I'm just gonna show you the Tata specific UV printing service things that you'll need to do. They do have it written up, but it's nice to just see it because if you don't do it correctly, you'll obviously screw a lot of things up and you'll waste all this money and blah, blah, blah. So starting off, you can come up here and just search whatever enclosure you pick. So I did the 125B and then I'm just gonna say UV. So you can see it's like the drill where it's $4, but then gets cheaper the more you add. Down here, it'll just say about ordering it, which I will go over later. But the way to get to that like guide thing I was talking about is you can go to the hardwares and tools, hit enclosures, or just probably anything, because then we just want to hit this enclosure UV printing service, and then this will pop up right here. So you can read through this. You actually absolutely should read through this. I am going to go over a lot of it, but the first thing to do would just be to see which enclosure you got and then download the Adobe Illustrator file for it. If you don't have Adobe Illustrator, you can use Affinity Designer, but from what I've heard and they say here, it's not like directly supported. There are a few videos that I can link, or maybe one video I think of somebody showing how to do that, but Adobe Illustrator works great. So I'm going to teach that here. You can just like do a subscription for a month or something and get it. It's not horrible, but yeah, just download the Adobe Illustrator file. And while you're at that, scroll down a little bit and download this roll-in swatch. It is something that we will need for colors and things, so definitely get that too. So now here I am in my template. This is nice. They just have it with the exact millimeters and the specific layers that you need. You'll see here we have white, color, and gloss, the varnish or matte gloss. That is an additional service that you can order through Tata. If you just search up here something like gloss, you'll see that it is an additional price, so an additional $2 unless you order 50 plus, then it's $1, and this will order the gloss, and then you have to say that on the checkout, and then that's where I think you pick what type of gloss you want. For this pedal that I had done, I did use the gloss, the varnish gloss. It looks great. It is obviously extra money. I would say that if you're just kind of making a one-off thing for yourself, might as well get it. It'll last a bit longer, kind of having that top part of it, but it's not needed. I've also done some without it, and it looks great either way. It just might chip away a little bit quicker. Either way, there is a special thing we will have to do with the gloss. Very simple, but a thing we will have to do. But for now, we can just ignore that. So the main thing with this, obviously, that we need to kind of take note of is where our actual knobs and everything are laid out. And I'm just going to show you like a little trick on how to do that within Illustrator if you've never done like exact millimeter measurements within it. Because if you have something like mine where I like write out the text below each knob or something, or your graphic just somehow refers to a button below it to the side or whatever, you will need to know where that is placed and hopefully somehow mark the overall diameter of that knob, LED, foot switch, whatever it is. So first thing I'm going to do is just get our drill schematic right open next to us here. And then we're going to need to just refer to a ton of these. I'll stretch that out so it fits. So coming over in Illustrator, the main tool I will obviously be using to make all these knobs is the ellipse. You can just right click this, select the ellipse tool, and then if I hold shift and place, it'll be a perfect circle. Doesn't matter, don't worry about the size. You don't need to read those little millimeter markings, just let go, and then we can come over to properties and set that. The thing here to note is that the drill diameter is not exactly going to be the whole diameter that you want. That really comes down to the caps that you're going to put over your knobs, or really any of your devices or things like the nuts and washers that sit over it. That's the real thing that we need to keep note of, because obviously those will be a good amount bigger than these actual drill numbers here. So using all of this detective work we've done so far in this course, somehow in data sheets or one way or another, find out what the actual diameter of the thing you have. I have these knob caps that I 3D modeled and designed and printed, which I will link on Maker World in the description, but I know if I were to just measure this right here with a caliper, it says they are about 12.7 in diameter, so I'm going to make this right here 12.7. And those will link up and be fine. So how these ellipses work is the center of this will be this X and Y coordinates right here, which is quite helpful. So when we move this, we know that the center is there, and that's the same with all of these. The center will be that X and Y. But the annoying thing is that if you see, I'll place this in the top left, and the top left in Adobe Illustrator is 0, 0, whereas the middle here is 0, 0. There's another annoying thing, which is that when I go down, you'll see my Y gets greater, whereas in here, if you go up, your Y gets greater. So the little trick that I always do is I'll just put some object I have in the center, this ellipse, and now we can see what our 0, 0 on the drill schematic is in Adobe Illustrator, and then just do some very simple math. Right here we can see we have 31 as our X, 58.5 as our Y. And then that just means over here, whatever this value is, we just need to take that X and then add this value to it. So in this case, we do 31 plus negative 20.3. So that would be 31 minus 20.3. I'm going to just get my calculator. 31 minus 20.3 is 10.7. So I'll set this to 10.7. And then since the Y is the opposite, we want to subtract the Y value from this. So the Y is 58.5, and then I will subtract 38.1, and I get 20.4. So let me just put 20.4, and there we go. So that's placed exactly how this is. You might be thinking, why can't I just take a screenshot of this and overlay it? And it's a good thought, but you'll very quickly see why that won't work. And that's because, as they say here, the form is for illustration purposes only, so it's not exact at all. Like, this is not at all the same even ratio of resolution. If your graphic doesn't like super need to be exact, this could be a quick way to just quickly kind of know the general place where the knobs are. I have done that before. I've made some graphics that are supposed to just kind of be a cool image overlaid, but this is quick enough, so might as well do it. Another thing I should have done is not put this on our color layer or any of these layers. So I'm going to add a new one, and I'll just say like drill, I don't know. Put that at the top, and then I'm going to move this ellipse in there so we can get that all off of color and just turn this off and on when we want. We will want to hide this or something or delete it and do a separate version when we turn it into data, but for now it's totally fine. So that's it for placing them. I'm not going to go over myself doing all of them because it's the same thing for each of them. So hopefully that makes sense and you can set those up. Now the next thing is dealing with colors. So here's this final version that I used for this. You can get this in the description if you want to use it for some reason. But I'm just gonna, instead of like showing me make all of this, I just wanted it to look cute and have stuff from the course and audio programming things. But there are a few things I'll show that you have to do if you were to make something like this. So one thing I did that made my life very easy, but obviously is at the price of not as cool of a design, is that this is just completely black and white. So for this pedal, I just ordered the 125B that was already white, and then I just had to print the black over it, so I didn't have to worry about doing some of the things that I'll show that you need to do. I did have the gloss layer, which has this weird color, which I'll show later, but yeah, if you are just trying to do a pedal that is just black, then it's a lot easier. But the other stuff with color is not like a lot harder. It's just like a little extra step we have to do. But one thing that you'll need to do for all of these images, text, everything, is you have to vectorize them, because that's how these machines kind of program and use and paint on everything. Basically, like, here is this random Apple Music logo I have, and right now this is not vectorized at all. You would know if it is because you can take each individual aspect of something. Like here, you can see how these aren't touching that, so this is actually its own object that I'm able to move, whereas obviously this is just one full complete thing. So one of the main ways to do that is this image trace. This won't be a great solution for a lot of things, but in this case, I wanted everything to be black and white, so I can just hit this black and white here, and then if I just change this threshold to be more or less, you'll see that'll start to do this. In this case, this was like a pretty low resolution image, so it's having kind of weird distortion, but you get the idea. Now, if I were to hit expand here, now this is vectorized. Everything is still like grouped together, but if I come over here and select this selection tool, I should be able to grab this. But then you'll notice that there is all this white, and this comes back to the color thing. So one of our layers here you'll see is white, and that means that literally everything in your image that is white needs to be on this layer and cannot be in the color layer. So in the case of this would not work at all. I don't know exactly what wrong it would produce, but it would not be good. So one thing I like to do, since if I were to do this a lot of times, so let's take, I have all these little icons of things. Okay, Instagram logo for some reason. So now let's do that same thing, image trace. I can make that a little better. There we go, hit expand. And now this will also have produced this white right here. So what I typically do after doing all that is I'll just select that white. Since this is like pure white, they're the exact same shade of the exact same color, and I can come down to select same, fill color, and now it will select all those other whites, and I can just hit delete. So now we just should have this right here, and you can check by just kind of moving some other object over them, and that'll work great. Say that you didn't have a white background like I do, and you actually needed maybe this to be white. Well, then we come over here and we obviously just need to move that to the white layer. So I could maybe just Command X and then select this and Command V. So now we have this white right here. You can't really see because I have white on that layer, but this is just the white. And now this is where we have to deal with swatches, which are just like different colors. And that's where we have to upload that other .ai file that we had gotten, the Rolla VersaWorks. And we can do that by just going to Window, hitting swatches, and then this one already has it. But if you come down to this library and then you hit other library, you can now select that file. So I can come here, select the Rollin one, and it will open those swatches right here, which then they should just be listed down there. So if you just kind of hover over them, you'll see which each one should be. You can just look at these ones here, and you'll see one that says RDG white. So this one, you just have to have your white object selected. So all the whites in the white layer, and then just click this, and now that will work. It won't look white, but it will be the correct thing that you need for the UV print to work. On the topic of white, another thing that you will have to do, which they have a really good example of this here, is if you have a dark petal. So if you ordered one that has a black background or maybe just some other dark color, if you were to put bright images on top of that, it will look like this. So what you have to do is put a white undercoat. So just take that exact, say that this guitar was the exact examples of this. So say the guitar was like this orange and the pedal this time was black. I can come down here. I'll make that just a different color just to make it look better. Okay, so say this is that color, and now I have this black pedal in the background. Well, what I want to do is just copy that layer, put it on the white. Obviously, you'll want it to match up. There we go. And now I'll just need to make the thing on the white layer, obviously that RDG white. There we go. So now if I took off this color, you'll see that I have that guitar under there with the correct white. So the next thing is about overlapping colors. This again just comes down to the process that happens when you UV print. But say I have this folder, for instance, and I'm just going to duplicate that and say that this folder was red and this one was blue, and I had them overlaid like that on top of each other. This would not work. Or it would print, but it would have unwanted results because it would print this blue and then it would print the red over it, and these colors would get jumbled, and this would probably look weird. I'm not exactly sure, but it wouldn't work. So what we need to do is actually cut out the part that overlaps so that it just doesn't exist at all. And that's very easy to do in Illustrator. So I can just select these two, and we want this Pathfinder tool. I don't know if it's default shows there, but you can probably come down here, say Window, and here we go, Pathfinder, or Shift Command F9. So then we have this Pathfinder window, and the quickest way is you can just hit merge. So now if I move this red, you'll see the blue doesn't have that, and it will just look exactly how it did, but there will not be any overlapping colors. Another thing is you need your Illustrator file set up in CMYK mode instead of RGB. I honestly don't know enough about color stuff to tell you anything why that is or what that changes, but make sure you have that set. Another thing I'll just show real quick is if you have text like this, you also need to vectorize text. So say, for example, I come here and I have some text. Right now, this is just a text object or whatever, so it's not vectorized at all. I can't take each individual letter and do anything like I can here. So what you have to do is select it, right click, and hit create outlines. And now this will be vectorized. Make sure if you're doing this, either make sure that it's good and you like it, or I would just create a backup, maybe an entire backup layer or just that exact one, because now I can't go in and easily edit the text or the font, or I can't do it at all, in fact. So I would create a backup, don't do destructive editing, and that should be fine. So now the gloss layer, basically we have to do the same thing as we do with the white layer, but it's even a little bit easier. Because say you just wanted your entire image to be gloss, you can just duplicate everything in the color layer. Like I can come up here, say duplicate color. Imagine this was their blank one. Obviously I already did this, but I could just delete that. And as long as it is named the correct thing, so you can say gloss dash V or M, whether you want the glossy or the matte. And now I just have to select all of these, no matter what color they are. I know mine's black and white, but you just do that. We go back to our swatches, go there, select that, or if you've had them added, and now you just find this RDG gloss and it will make that all there. It's seeming like for this object, it is selecting the swatch for the actual fill, whereas I want it to be the stroke. So maybe that's just something to keep note of. Some of them might fill in things, so you'll get these unwanted results. So you'll need to select it and actually fill in the stroke instead of the fill. So here's this fun example. This is one of the first petals I UV printed on. This is a joke one for a friend. He really likes the Goofy movie. But you'll see here everything is vectorized and not overlapping at all. So letters like this are actually cut out at the bottom. That's just the white layer there. But yeah, nothing intersects completely. And then here I ended up just duplicating everything and then putting white under there, and it worked. I haven't honestly done a color petal in a while. I really like just the black look, but maybe this is the way for the color to just put the white underneath. It's a pretty light blue petal, so I didn't need to do it for the dark reasons, but I think I was just confused at the time with things like the skin color, and it did come back like a little red like these ones here. But yeah, this totally worked. The eyes and everything are super white when it printed and everything. So maybe that's one solution, is just to put a white layer of your whole thing. I'm not totally sure, but it worked for me here. And I even had this in RGB, which is probably honestly why the colors are just like a little bit off. So I think I definitely should have fixed that and noticed. In terms of saving everything, you don't upload the .ai file. What you need to do is export this as an Adobe PDF. You can just select that here. So I'll just select coarse petal, replace that because I had it. And then I guess selecting high quality print or the default is probably fine. Export that. And it should just look like probably just all the gloss if you put the gloss on it, and that's good. Here, the reason you could see the white, if you remember, I had duplicated that. That was just testing stuff. Obviously, this is all testing stuff, but yours will probably just be totally white, like the one I just showed you, or totally this color like this here. This is all just that. In this case, I would have probably hit save as and made my sort of copy of this that I actually want to distribute, and then done things like come here and delete that icons layer just so I can only submit those three, and then export that again. And then to just make sure everything is fine, because I know it's kind of nerve-wracking, you're spending your money, you can just go to that PDF file and do right click, open with Illustrator, and it should pop up with all your layers. This was before I deleted the icons, but yeah, it should just pop up fine like that, and then you're all good. There are a few more things on here, like how to print on different sides, or just like what to add to your cart. Certain colors like here, gold and silver, doesn't work. So I would still just always recommend to read through this before you do anything. So now if you actually want to order this, you need to have in your cart all of the different things. So like I would need to have added that original UV service here. So I would add this. You will have to add extra ones if you want to print on the sides. And then I would also need to add the gloss. So here's the extra gloss, and then 125B drill. I would need to add that. Plus if you want anything on the lid. And now we can come over to the drill tool, and we already have that drill template here, but you'll need to start your new UV template and then just call this whatever, coarse petal, select your enclosure type, select the side it's on. A is just the face of it. And then, yeah, it's pretty self-explanatory. Do we have data in the color layer? Yes, 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 yes. And now this is just going to ask you questions to just make sure. So it's saying, do you have the correct stuff from the swatches we do? Do you have any data in the gloss layer? Yes, we did. Did you do this correctly? Yes. Select the type. We'll say varnish. And now this is where you can upload your file, check all of these, and then save the design. I already have that design uploaded like here. I didn't have data in the white layer, so I said no to that, but you might. And then when you actually order and purchase everything, it'll pop up right here in this section. And since I have already ordered all of this, I can't show you exactly how that screen looks, but it will just kind of prompt for you to select if you had gloss, and then it will make sure that you had actually purchased that and the drill. And then you'll just select the template and the UV print, and you can submit that. And then in a couple of weeks, you'll get it. By now, you might already have bought some knobs and things, or I've talked a lot about those right angle knobs, and I have all those SKU numbers. But remember, you also do need a resistor for those LEDs. So if you're just doing that exact PCB we're designing or something similar, make sure you pick up those resistors. I just use 1K ones for the Daisy, and that works great. And then also your audio jacks, your DC jack, foot switch. Again, I will have all the SKU numbers for Tata Electronics of all the ones that I use, but a lot of these you can use your own parts. Just obviously, again, make sure that your diameters and your drill schematic match that. We did it. We got all of our parts ordered, made, built, shipped to us, and now we are ready to put it together. So really the last remaining thing is to solder it all. So if you already know how to solder, which I kind of assume a lot of you do, don't worry, I'm not teaching in this video how to solder, because honestly there are already so many resources out there that anything I'm going to say is basically redundant. So if you literally have never soldered before, I recommend to just Google and find any YouTube video teaching you. What we're doing is pretty simple, minimal through-hole soldering, so there's not going to be this big learning curve. It's pretty simple, even though it might seem daunting with lead and high heats and everything. You're not going to hurt yourself. It's fine. Make sure you have good airflow and you'll be good. I do have the first soldering iron I ever bought. It was like 20 bucks. I think some of those, if you're like totally just getting started, are totally fine. You don't have to go spend 100 bucks. I have a slightly better one now. But if you're seriously just starting out, don't go spending a ton of money. So instead with this video, I'm going to give you just some tips for soldering together the pedals specifically, and then sort of some going forward tips. As we know, this course was sponsored by PCBWay, which earlier we ordered our PCB from. But on top of that, I also wanted to show you how using their custom CNC machining, we can make even a cooler custom pedal that will cost a lot more money than doing something like Tata, but then you can make your own completely custom shapes, and it's pretty awesome. So in this video, I'm going to show you just pretty quickly some of my process for making this custom pedal. It's not like a super custom shape. I just did the 1590B kind of standard size, but it's a smaller pedal. So I wanted to show you how we could maybe make PCBs for scaling down to smaller sizes or anything, just to give you some ideas going forward. But I'm going to do it a little backwards since you might be at the point where you're just ready to solder. So here are just some basic tips for you if you're going to solder your pedal right now. So here's most of my tools here for the pedal. We got our soldering iron. This is the TS101, I believe, from the company Miniware. I got some helping hands, steel wool. We got our little sponge under here, and then I have the pedal totally soldered. So I have already done this, but I'll still show you tips using this new one I have. And then I got the Daisy right here, headers. This is the enclosure I got custom CNC'd. I'll give you the story on that soon. And then here's the PCB I will be using for this pedal right here. So in terms of all the tools you will like totally need for this, obviously you need your soldering iron with your sponge, steel wool for cleaning the tip. I would say helping hands are pretty required, maybe not this one exactly. These are super cheap. You can get these anywhere, but just any sort of way to sort of prop up things. I'll give you a little tip on soldering some of the jacks and stuff. But yeah, some way to obviously hold the PCB while you solder things on. In addition to that, you'll see that we actually have wires in here. So these jacks and the foot switch are all actually wired into the PCB. So I do have a big thing of stranded wire and solid wire. The difference is the stranded wire will be much more flimsy and bendable because it's just a ton of little wires in there, while the solid one is like more like those jumper cables we had where they're just one little more solid wire. Stranded would be better for this because we want to be able to squish it and push it down and fit it in a smaller space. So I do recommend stranded. They're a little bit more annoying starting off because you will need to sort of make sure the tip can actually fit in the holes, and it's sort of annoying, but it will be better overall so we can squish it, especially since there are some wires under the Daisy itself in this design. Because we're working with wires, wire strippers are very helpful. You can use scissors or wire cutters to strip the wire. I don't totally recommend it, especially with stranded wire. You might cut some of the little wires off. So I just have these wire strippers right here, very standard. You can choose the size. These also have wire cutters in them, so I don't need both, but I do have my own pair of wire cutters. I got the Daisy right here. I got some headers I'm gonna use that are smaller than the ones you might have. These ones are sort of low profile headers. The point is for this pretty small pedal, I need to be able to really fit it in there, whereas these ones have the bigger headers, so I can put wires under there. So it's just different designs. So first tip I want to just give is, if you bought the unsoldered Daisy like I did, I really recommend that when you solder on your headers, you don't just put them in like this and then set it down like that and then solder on that, because you'll find that you can make these headers uneven because you'll see they're really wobbly and you don't want to have them bent in any sort of way. So the best way to do this would be to just get your breadboard and actually just stick it in there. You could also just put your headers down and do that too. So now when I solder this, I know that the spacing is already perfect and it can't really move around that much because it's in the breadboard itself. So here I am, I got my defumigator on, soldering iron, which is heated up. I have this nice little 3D print here so that I can just nicely pull solder. Got the solder on there. Got the Daisy. And one little tip I'll give if you're starting off, just because for some reason I didn't realize this until later, your sponge should not be dripping wet, and it definitely shouldn't be dry. I don't know why this took me a while. I used to just like wet it a ton and then just put it down, but you should wet it and then wring it out, and then that will be perfect. So it should not be dripping water, but it definitely should not be dry. So now I'm ready to solder this together. So there we go. I put all the low profile headers on here and it's looking good. I can take that off and it is perfect. So next step is to solder all of our parts, obviously. And there is an order that you should do this stuff in that will just cause the least amount of headache. Kind of some of the rules I guess I follow are to try and do whatever is lowest first to highest, like in terms of the actual height of the component. You'll find that that'll create the least amount of headaches, because if you have some part that is towering over and you're trying to solder something that is smaller, it'll be annoying to try and fit your soldering iron in there, and you don't want to accidentally touch anything or burn it. Another general rule when you put the Daisy in and you solder your headers, we do want to do the same trick as earlier when we soldered the Daisy, where we actually should put our headers in. So I don't have any 20 pin ones lying around, but here's a 40 pin and I could cut this. And I would want to actually put these in there with the Daisy seated on top before I solder it in. That's kind of another thing just to make sure our headers are straight. So here I would take this header and put it on, and this other one, and then instead of just soldering that like that wibbly wobbly, I would want to put the Daisy on and then solder that. So that's something to keep note. And also, if you're just wondering the point of the headers, the point is that if the Daisy craps itself, or if we just want to move it to a different pedal, then we can, since a $30 component is cheap for the Daisy, but actually pretty expensive relative to the other parts. So if something happens with it, we want to be able to easily pop it out instead of desoldering 40 pins. That would be very obnoxious. So it's just a nice kind of fail safe. And honestly, like once you have more pedals, I'm constantly kind of moving Daisies around to test things so I don't have to constantly rebuy Daisies. But yeah, first thing I would recommend something like the resistor. That is an easy first off one. Another thing you'll notice is I do have this capacitor here, which I didn't show in the course. I was kind of Googling around about easy ways to have a little bit less noise. And I read online, somebody said putting a 1000 microfarad capacitor would reduce noise by like 50%. And when I tested that in a DAW, I found that that was true. So now I kind of just always do that on my really basic builds. The ones that I don't want to put much more else, I just throw that there. I didn't teach that here. You can kind of Google that for yourself, and they're pretty easy to just add on to your PCB. But yeah, I would definitely just solder the resistor on here first. And I typically do all the wires at the exact same time, just because that is a somewhat different workflow, so it's nice to just do that all at once. Another big thing to remember before soldering anything is the actual orientation of which side you're soldering which parts on, because they are different. With this example of the pedal I made during the course, everything is soldered on the one side except the pots, which are soldered on this side. So the side here that we're kind of looking at on KiCad, that's the side I actually solder on certain things like the LEDs. The pots, it seems here, I also just did the foot switch on that side. It doesn't totally matter. You can solder on either side. That's part of the point of through hole in this. But yeah, you need to note that, because like obviously if I accidentally soldered the Daisy on the other side before looking at it, then it would not fit at all, which is different. Something like this pedal, I actually do have the Daisy facing that way. So I'm going to solder the Daisy pins here. The Daisy will be facing this front face. So it is the opposite of that one. So you want to really pay attention to these things, because desoldering kind of sucks, and I don't recommend that you reach that point. So make sure you double check everything. So here we are. I placed the three sort of smallest components here, and then on the other side, this is typically what you do. is I just bend back the pins so that they stay in, and then I can come here and clip that into my helping hand and solder that. One little tip I'm going to give for people who are new to soldering and might avoid is if you learn about flux in videos, but it seems a bit complicated, and then you learn that there is solder like this solder right here, which has a rosin core, meaning it has flux in it. I honestly do recommend starting off that you just get a flux syringe or get more, because it honestly makes soldering so much easier. But I'm a bit hypocritical saying that because I have actually ran out of my flux, so I don't have any here to use today. But I think it makes soldering starting off a lot easier, which is kind of ironic because I feel like a lot of times beginners avoid it because it just seems like one extra step. But I think it just makes your solder joints just work a lot better. So I recommend that even in combo with the rosin core. Rosin core doesn't completely replace flux, but it will like do the job. Like I'll be able to solder these all together. But yeah, I recommend just looking into it. It's cheap. You can get it right on Amazon. So yeah. So there we go, I soldered it together, and forgot to mention that beforehand I did get open on my computer over there KiCad and my 3D model of this, just as another way to double check, since I had done all of that triple checking when I made this. It's a good way to make sure you're soldering it right, is to just refer to that. If you have bigger parts, you will obviously need just bigger sheets written out with these sort of keys. So like here, that was C2 and C1, and I gotta say, okay, which one is that? Pretty obvious here, because one is radial and one is a disc one. But if you have a ton of parts, you will need to go and look and see which ones you actually need to solder, especially like resistor values or something. But hopefully that's pretty self-explanatory. Now I'm just going to snip off these pins. So next, I think I'm going to put the headers in, because this pedal has really tight clearance. Pretty much on the 3D model, the pots are like overlapping with the Daisy, but it was just so little that I'm really hoping it'll actually still work. I still don't really know, but I'm hoping for it. So I got to do the Daisy first before I solder any pots or anything, because I want to make sure I can squeeze it in there. So I'm going to do that little header trick, making sure to note the orientation to actually solder it onto. So here I got the Daisy with the headers in there. And another trick here, because now these are not soldered in yet, but I need to, and one trick is you can just get like styrofoam and then just like push it into it. Something like with the Daisy, I might take this little cap off so the pins will actually stick in there. I don't have any styrofoam right now, but I do find that I can also just pretty much set it down like that. Maybe hook up one little helping hand to stabilize it, but I can feel that all the pins are not moving around and they're very even, so that like should be good enough. All right, I got the headers for the Daisy soldered on there. And now for the rest of the build, I do recommend just taking it off because you don't want to accidentally hit it or anything. But yeah, now we can move on to the pots. So first thing you're going to want to do when you get your pots is notice this little tab on the left or right of your pot. Zoom in. So you see this little tab right here. This is for locking pots in place. It's actually a very handy feature, but with our enclosure and the way we did this, we did not utilize this. So we actually need to take some wire cutters and cut it right off. Now I could just go here and push really tight, but this piece sometimes just goes completely flying. So I like to just like put it under something. So here I'm gonna put it under there, squeeze tight. It still went flying. So maybe put it in a bigger thing. But yeah, we do need to snip all of those off of our pots. So my big tip for the potentiometers is we want to actually put them in the holes before we solder on. First, you want to see the actual orientation. Like here in this one, they're sticking up, but these are actually like backwards. So this is the way that this pedal is going to go in here, and you see the pots are pointing down. The one that we made throughout the course is the opposite. So these would be pointing this way. You can do it either way, obviously. It's just all depending on how you're going to fit it in there. But for this pedal, I had to do it this way, which means in the code, I'm going to have to invert everything. But yeah, then we want to actually put it in the holes. But you might notice it would be really annoying for me to put it in here, because then we're going to fight with the walls of the enclosure. So I typically just put it on the face, and I can pop that in. And now I have the perfect surface for me to solder on all these pots. It will definitely fit because they are already fitted. And yeah, it's a very handy way to do things. All right, once you've done that, we can pretty much do the exact same thing for the LED. You just really need to make note of which leg is which. Typically with LEDs, the short leg is the cathode, which means that's what goes to ground, and it's also the side with the flat side of it. So I can just put the LED in with the correct orientation, just pop all that in, and then I gotta make sure everything's flush. I actually went and put the Daisy in because in this build, the Daisy is just a little bit taller than the pots, which will create some annoyances, but either way, I want to make sure my LED is coordinated with that. So there it is. I have just a little bit to solder on, but it should be fine, I think, in the end. So I'm going to solder that on right now. All right, so there is the somewhat easier part done before the wires. This has actually ended up working out. I had mentioned that some of the clearances on Fusion 360 were a bit odd here, so you can kind of see they're a little crooked, but it was as I hoped, and it did kind of just push over. I also accidentally soldered a knob with a slightly different shaft than these, which is fine. I don't really care to desolder it. I have caps for that. It'll just look a little bit different, but yes, it's coming out well. And at this point, you could just check to make sure everything fits correctly in the actual housing. So you could kind of pop that in, and there we go. And now everything is good there. You might have to kind of finagle the pots a lot of the time, but it should work at this point before we do any of the wires. So before we do all the wires, meaning the 2 jacks, the DC jack, and the foot switch, there is an annoying thing about the DC jack that you will need to know. You'll see here, if you look at the DC jack that I use and linked down below, the actual screw for it is on the inside, which means that to actually screw this onto the housing, we had to have it in and then screw it, which if you think about that means that we have to have the wires already soldered onto the PCB once we put the jack in there. It's very annoying. There are many ways around this. The main one that I do a lot of the time are screw terminals. Here's an example of a screw terminal right here. So instead of directly soldering on the actual wires, you just stick them in there after crimping them in this certain way. And so if I wanted to, I could unscrew these right here and pull those out and then take the PCB out. So this is something that you just put another different footprint on, but for this pedal, it couldn't fit, sadly. The screw terminal was a bit too high for having it on the back side of here when I put it in, which was unfortunate. And then I decided not to teach it in the course just because it was kind of one extra tool you need. Like here, I have this tool for the screw terminals and then a whole little pack of things. And I wanted stuff to kind of be the least complex as possible, which does mean that there's this annoyance of having to get your stuff wired on before you actually fit it. And so yeah, what I typically do then to kind of compensate for that is I put on like pretty long wires for the jack, not crazy long. And also for this being power, you don't want it to be like way too long, but I just put it long enough so that I could maybe have the PCB sitting out from it just a little bit. In the case of this design, I have the power jacks all the way up there, like the holes for it. So I'll need the wires to at least be that big, and then I might add on like 50% of that or even double sometimes because I have plenty of space here to fit the wires in. And yeah, it's not a huge deal, but you will need to make sure that the wires come from here, go through the hole, and then go to your PCB. This has to do with like grounding stuff and everything. You can't have the metal from the DC jack just directly on here and touching that. So yeah, it's a simple problem. So next we're gonna have to use wire to cut and solder onto our parts and then solder onto the PCB. There's some simple tips for this. It's like a little more annoying to do or just more tedious to do than obviously just directly soldering onto the PCB. But here I have some 22 gauge stranded wire. I'm missing black, but normally I would do that for ground and then red for power. So I'll just use like yellow for ground or maybe blue. So I can just take a certain amount out and you can kind of roughly measure. I mean, you can just sort of eyeball it. So I know that I want to make this one a little bit bigger. So I'm gonna make it like that big and then I cut and now we can come and strip it. Now stranded wire, it's like a little more annoying to work with than solid wire. But yeah, in the case of something like this, there are these tiny little holes on it that you maybe can't see. Yeah, there are those little holes, and those are like a little too small for me to probably be able to fit this through. I can try, but the first step is we need to tin this wire. All right, this is Sam from the future. Unfortunately, this little tip I shot was like super out of focus, like some other ones were. Apologies for that. But this one specifically, kind of wanted to show it off because I think it's a really helpful tip that saved me a lot of time, a lot of effort. So yeah, it's just on tinning your wire. I'm gonna just strip this wire first. So here's stranded wire. Like I mentioned, it's a bunch of just mini little wires within it. And we need to tin this, which is basically cover it in solder so that it kind of looks like those solid core ones and it's one just like continuous little pin looking thing. The reason for this is to just sort of prevent like fraying, it creates a better connection, and it will just be a lot easier to kind of stick into PCBs and other parts that we want to solder it to. So first step is that we just want to twist it so that it's kind of a nicer little point to work with. So there we go. Now I'm just going to clip this into my little hands right here. So before I learned this little tip, what I used to do is just kind of take the soldering iron on one side, and on the other side I just feed in solder and then kind of move them both together. And that works, but you'll notice you get a lot of sort of like clumps that you might have to cut off, or sometimes I'll just kind of cut the section I just soldered off and redo it, because then it won't fit in your PCB hole or anything. It's really annoying to work with. So this tip, basically, if I just get my clean soldering iron here, is basically we want to just put like a little dab of solder onto our tip here, and then just press that and hold against the end of the wire so that we can just directly feed solder onto it once it is warm enough. There we go. Took a second. There we go. And then boom. Now we're good. You'll see in the edge it kind of flared up, and that happens a lot, and whether it does or not, I just typically cut the end off like that, and then sometimes I will come in, or almost all the time, I'll come in with some needle nose pliers and just sort of flatten it out, because even once you cut with the wire cutters, it might kind of flare up on one side, and that can be annoying to work with. But yeah, it's just basically we want to feed the solder in once the wire heats up from the soldering iron there. That took like a little bit for me. Maybe I could have put more solder, not really sure. Sometimes having like a thicker soldering tip at the end, like your soldering iron tip, will help, but that creates a pretty perfect little tinned wire there. And yeah, there's like a name for what that is. I don't really remember offhand. Maybe I'll flash it on the screen here, but really helpful tip. I'm super glad I was taught that in school. So yeah, definitely recommend you tin your wires that way. And yeah, this one does fit right in the hole if I push like that. So there we go, that goes through, and then I can bend that a little bit and solder it. I might do it from this direction, but there we go. There is the power side of this jack soldered on. I can probably even cut this little excess. And later I will show you how to put heat sinks on this. It's something that again is not required. You can see some here. This is actually because I soldered two wires together, because I had to take this out and do some repairs, so I actually had to cut that there. But yeah, it's a way to just kind of keep the joints safe. It's really for heat stuff, but for this it doesn't really matter as much, but just a way to make sure that our little delicate soldering job stays. But yeah, I'm now going to go through and solder the wires on all the parts. It saves a little bit of time if you do each step at the same time. So before soldering this onto the PCB, I can do the foot switch and these two jacks, and that'll just save us a little time in the long run. Here are the jacks I'm going to use for this build. These are the ones that you might be using for yours. Once again, you need to kind of look and see which one is ground and which one is the signal. We had done this earlier, so hopefully you know by now, because you would have had to have used jacks if you used a breadboard, but typically the one with the kind of bigger arch is your tip, which is your signal. You can also look by actually looking inside. You'll typically see some sort of thing poke out, and that is the actual thing that's going to touch your tip of the jack. Like if I get a cable over here and plug it in, you can't really see it on the camera, but that part of that is touching the tip. It is sort of locked in there, and then we can follow that metal to see that that is this piece. Then there are sort of tinier jacks like this one where you can see that very much firsthand. So this is going to be our tip or our signal. So next thing I wanted to show you somewhat briefly, because this is an optional step, are those heat shrink things I was talking about. I'm going to do that just on this DC jack just for some extra protection. But you see here I have this set of heat shrink tubing, and you can see there's just all these colors with different sizes. And the point of this is to just sort of protect everything. You'll see this in some higher quality builds. And then what we do basically is take a heat gun, and after I put the tubing on, I can just put that under the heat gun and it will shrink. You can also use like a lighter or even a soldering iron sometimes. The heat gun is definitely the best way. The other ways you'll have to do a little bit more. You'll have to be a little bit more careful, but and we can see that has already just completely hugged and wrapped around. And there you go. You can see it is now completely just hugging the pins for a nice secure connection that is definitely not coming undone. So now I got my foot switch, 2 audio jacks, and my DC jack all soldered together. So it's time to solder it onto the PCB. The only tip here is just to do that jack last, since you'll have to actually connect it up to the enclosure while the PCB sits outside of it. So it'd be annoying to do that first, but yeah, should be simple enough. Just make sure you kind of have the side picked out. Like here, all of my pins are sort of inside the Daisy margins here. So instead of having the wires feed all the way under, I can just have it on top. But that's because my Daisy, in this example, as I've said many times, is facing the face of it. Whereas for this build, I actually put the wires under it because that is less annoying than having it under the entire PCB. So yeah, I would solder it, make sure your Daisy's not on there, and then when you fit the Daisy on, you can kind of just move the wires out of the way. It's not that hard. So here I just tinned the tip of this one audio jack right here. So I did that thing we did earlier, just rubbing some solder quickly over the wire, and then I was able to just push it right through the pins, bend them a bit, and solder them as we have with the normal parts. All right, so I soldered the 2 jacks and foot switch, so now it is time to do the DC jack. So like I said, you will need to, where's my hole? There's the hole for this one. So I need to feed it through this, pull it all the way through, and then you got to put the screw on. So I got to take these 2 legs. And this is something to just even note when you're soldering. This is the pins here you want to be pretty well kept so that it's easier for you to put this screw on. Because I've had times where I have had to kind of bend things, but this went on pretty well, and now you can just screw that in before you solder. All right, I got the jack all soldered, and now I'm ready to assemble. One other little tip, in case you run into troubles doing this, I know I have many times in my days of doing these pedals, especially just like, I play music while I solder. It's just like a kind of peaceful experience, but sometimes it makes you not pay attention, and I will solder like a ground wire into the signal and vice versa, and you'll have to desolder, and that definitely happens. I do recommend to get a proper solder sucker like this one. Like I used to have one of the ones that just came in those kits, like when my first soldering iron was like $20 for a kit, and it came with one in it, and I used to think they were just pretty unusable because the one I had was just bad. So I went and bought, this is Viraloy one, and this works great, and kind of just searching up more proper techniques on how to use it, and they're very fun to use. So recommend that. Hopefully you don't screw up anything too bad. So maybe on like a jack, if I soldered them the opposite way, I could just probably hold this while being very careful and put the soldering iron on the wire and maybe just use 2 fingers to pull it out. That would work quite well typically. You might find that when you put your tip to the solder joint that it doesn't actually liquefy. And the best tip there is you should actually put some solder on your soldering iron before you go there, because the solder will help it liquefy a lot better. You might need a higher temp. Sometimes desoldering, I'll need to turn the temperature up. I wouldn't do that first thing. I would just put solder on the tip, and that works for me like 90% of the time. If it is a wire, that is definitely best case scenario because you can easily pull it off. Something like a pot would take a harder bit of desoldering because you have 3 pins and they would all need to be liquefied when you pull it out. Sometimes you could take like a longer wire that you lay against all 3 and you heat that up and then they all liquefy and you can pull it. But yeah, there's a lot of ways. If you had to do something like the entire Daisy, like say you didn't use headers for some reason, then again, you would probably need to lay some big thing across because it would be pretty long, tedious process for you to just go through and desolder joint by joint. But yeah, hopefully you've put enough sort of fail safes so that you don't do anything too destructive and you get your pedal done. But yeah, I'm ready to put this pedal together and start testing it. And we did it. Here is our pedal completely done. This is the one that I've been building this episode, and this is one from the course, obviously. This one I would just kind of push these little wires in and then just put the lid on. And this one is a little more compact and nicer, but yeah, these are completely done. So now we can kind of just test out and make sure everything works. I made this one to be sort of this Daisy development box because you can see here I actually put holes in for the boot and reset, and I have a little cutout for the micro USB. So I don't need to take the Daisy out to program it at all, but you will need to. So you will have to kind of pop this out and make sure when you do that, you don't rip it out from one side. The headers can bend. So you want to kind of equally pull from each side and pop that out so we can program it one last time. So you might have noticed by now this very odd looking laser engraving on my enclosure right here. And this is a very silly, stupid mistake I made when submitting my part to PCBWay. I custom ordered this part with the CNC machine services, and I had a little graphic that I wanted laser engraved on top of it. It's a cool way to just create a somewhat unique looking pedal that isn't just putting like a black graphic or something. It's this really light looking, nice texture sort of on top of it. But I was slightly confused by some directions, seeing as I've literally never in my life done anything CNC machine related. I've not touched this. That's why I've done some like basic 3D modeling with 3D printing, so I kind of understand that. But 3D printing and CNC machining are like almost the inverse of each other. You know, one's like creating it bottom to top. CNC machining is like all these axes rotating. I don't even know. But I saw that it said we needed multiple files for the sort of top graphic, one that is the graphic itself, and then another which is kind of showing them the area. Because the thing about PCBWay is this is like a pretty heavily automated site. You know, they aren't having all these people look through everything. You need your initial review, and then I assume it's just sent off to the machines. So I sent two graphics. One was my .ai file with my Adobe Illustrator thing, and the other was a DXF file. And that had just all of the little holes laid out, and then it said engraving area. And the point was I wanted to say like, hey, this is the side, this is the orientation that I want to be engraved. But I found out that first off, those probably should have just been combined. I could have just showed the holes on the graphic and they would have understood. But also I believe it is something about the fact that I had uploaded this file first and then the machine just sees that one and it goes. So when it was initially reviewed by a person, it was approved, but then eventually the machine just was given this one file. But I told them about this and they reached out, very apologetic, even though it was very much my fault, and they offered to send me a new one. I said no, because I don't want to just have to throw away this nice parts, and I think it's honestly kind of funny. But just a good thing to note when using any service like this, that you should triple check your work like we did earlier and just make sure of everything and make sure you understand it all. Luckily, when you're using a service like PCBWay, they were extremely kind about it. They didn't, even when I reached out, they didn't know that this was a sponsored thing or anything. I just reached out on my own and they were extremely kind about it. So you know you're in good hands ordering with them, but you do want to make sure that you get the right things to upload so you don't make the mistake that I did. Well, guys, we did it. We've made a guitar pedal, a custom, fully built pedal. The day has left us after hours of work. Our desks are all very dirty, but you know what we have over people with clean desks? We have a guitar pedal, and that's what matters. But unfortunately, just because you soldered everything together, it does not mean it's gonna work. So now you have the amazing process of just testing every single knob to make sure it works. As I said, hopefully by now you have taken your Daisy out and you gotta put some code on it. But I've held your hand this entire course by talking and going on way too long of tangents. So I'm going to hope that by now you can do this next part on your own. Obviously, up to this point, you may not have actually written code specific for the pin layout that you made your PCB. So now is your time to do so. You should be able to go and take that passcode that we wrote and just change the defines at the top and then flash that. But also on top of those changes with the foot switches, we now have an LED, which we did not use earlier. And that's something that I'm also going to leave to you. My helpful hint is to search up the GPIO on the DaisySP documentation. That is how you should initialize your LED. But if you get really stuck, I do have all the code available for this pedal specifically and the chorus pedal, but built for my PCB and the GitHub repo in the description. Some recommendations though for testing things is before like throwing something like your chorus or like something you wrote recently onto there, because maybe the problem would be actually with your code, you should throw something really simple that you can just one by one test each knob. What I typically do is just use the Daisy oscillator class, and then I map each knob to just the frequency of the oscillator because it's super audible to tell, and then just put the bypass to turning it on or off, and then you can join up the LED with the bypass and you can just test everything. You could have literally every single knob mapped to frequency and they all are just changing it. I think that's a really easy first way to test. Now, what happens if you turn a knob and it doesn't work or you get unexpected results? Well, first thing to do is double check your code, because that's the easier thing to debug, obviously. But it depends on what the issue is. If your knobs are going the opposite way as what you expected, then maybe you got your ground and powers mixed up in your PCB, or somehow you soldered it backwards. All you got to do is invert the data coming in your code. That's pretty easy. Foot switch, since that's not polarized, you should know that your wires are good, but you should also just double check your wiring of the PCB itself, because maybe you messed up a while ago in KiCad, so you should double check that. But first thing would just be to make sure you have your pins correct, because if just literally nothing, no data is coming from it, then that would be my first guess, is that you maybe just read which one wrong and you just mapped them to a different thing. But hopefully it works, you know, especially a pedal like this, it's only 3 knobs, so it should be simple enough. But yeah, if you're just like doing somebody else's design, like say you maybe just did this one, then obviously I would go to blame your code or the soldering first. The answer is probably not the PCB, but it can be. I mean, like I mentioned earlier, there can be internal things in your PCB that get messed up in shipping or something, but it's pretty rare. So I would blame yourself first. So some of you out there might be confused or let down that I went a whole video on how to build a pedal and I have not yet mentioned impedance or Ohm's law or buffers or any of that stuff. And I do have a reason for it. Hopefully you might agree that it was justified. If not, I am sorry. I might make a more in-depth tutorial on that in the future, but this was for complete beginners. And I figured if you could make an entire pedal that is unique and cool and sounds good and not need to dive into that stuff yet, then that is a positive. But it does mean that we have a few steps to go before we get to professional level or even like advanced beginner, because obviously what I taught here was more just like a little bit of everything on the stages, or mostly about just the kind of like enclosure manufacturing side, because I find that to just be like the most fun part of it. You know, making the art, figuring out how you want your knobs laid out, I think is a really satisfying way to start and get that inspiration before being overwhelmed with the world of electrical engineering. As somebody like me who in no way has an electrical engineering background, I took some classes in college, but yeah, I went to music school. So I just wanted to make guitar pedals at the end of the day. But for those wondering, impedance is an issue with the Daisy Seed. This is not something that you want to just avoid forever. So is impedance an issue with the Daisy Seed and guitar pedals? Yes. But was it a big enough issue that I thought that you should not make a pedal at all until you have it figured out? No. Technically, the DaisySP does want a low impedance input, whereas the guitar gives out a high one. What this means is you can basically expect some tone loss. Just certain voltages across the frequency spectrum will be lost due to this. But in my experience, it wasn't great enough that I don't think it's like not worth it to make a pedal without a buffer. A buffer is how we fix this impedance issues. If you are completely unfamiliar with these terms and these things, I would just start with learning Ohm's law, which kind of will explain a lot of the ratios of this stuff, because impedance is just dealing with that current and voltage and just kind of how they all relate, and it will help build your understanding. But you'll hear impedance described as AC resistance, or it's used with the letter Z. So a lot of like techniques and the foundations you learn from V equals IR will sort of apply to impedance and help you get that understanding of just like what is trying to draw power from what. But basically when we play our guitar that is generating voltage, typically I think in like the millivolts or something, our guitar, like it's not super high, maybe some pickups could get upwards of like half a volt, I think. But yeah, so we're sending that AC signal into the Daisy, and we just want a way for the two circuits to kind of not interfere with each other. We don't want one step to sort of step on the next step or draw power or current or whatever when we don't want it to. So what we do is we put a buffer in the middle of it. And these are like pretty simple circuits to understand. I think they just are kind of like confusing at first to kind of know where to look. But the two most common ways to make buffer circuits in pedals are typically with JFETs, which are a type of transistor, or operational amplifiers, also called op amps. Already with that, you can honestly go and just Google like op amp buffer circuit, or you can go on sites like Electro Smash, which will kind of break down famous pedals and you can see their buffer stage. But that doesn't mean that everything will apply one-to-one. There might be plenty of extra stuff that you don't need there. So the basics with specifically an op amp, because I've done the most with that, are what are called unity gain op amps, which are just like a certain configuration within an op amp. Because what op amps typically do is amplify your signal. There's this little equation with this variable A, which is like in an ideal scenario, this infinite number that is gonna like slam your audio up and then kind of clip it at what the power rails that you feed it are. Doesn't matter, but basically we want it to just match the exact voltage on the inputs and the outputs. So you do this way. If you Google it, I'll have maybe a photo here where you can route it'll look like a little negative that's considered the inverting input, and that'll just kind of be looping forward and connected with your output. And that basically just means that it will try and match the voltage at your input there with your output. And the effect of that is basically that coming into it can be a high impedance signal and it will give out a low impedance signal. And it kind of is just as simple as that, but there's a few things we should consider when designing a circuit with this. First is that for most of these op amps, you'll be using these pedals. They are what are called single supply op amps, meaning that they can't handle negative signals. So we have to do what's called bias the signal before it goes into the op amp. So if you imagine your signal voltage that is modulating, and it is modulating say like 50 millivolts to negative 50 millivolts, meaning it is going around zero, then you have all those negatives. So we just want to offset that by a certain amount so that it is still going up and down, but it's not going into negatives. And luckily this is pretty simple to do, but there's like a lot of different ways to do it. One simple way is that we can just take our 9 volts that comes from just like our DC jack we plug in, and we could just make a little voltage divider with just like 2 resistors. So I can take that 9 volt thing and put 2, like say 1 million ohm resistors in series. So after that first resistor, we'll get half of the voltage we're sending into this. So if it's 9 volts, we'll get 4.5, and then you have another resistor of the exact same value that goes to ground. So that'll just create your bias point, as they call it. You'll hear people call this like virtual ground or VREF in schematics. So that's something that can be helpful if you're looking at other schematics. You'll see, yeah, V ground, VREF, and that's typically referring to this bias point. So the voltage divider thing I just explained worked, but that won't be super stable. The voltage could fluctuate, so you'll want resistors that have a 1%, whatever that's called, whatever the word is, I'm forgetting. And then with a circuit like that, you also might see somebody throw a capacitor from that the V bias point to ground to just smooth that out and help with those kind of fluctuations that I described. But a more professional way to do it is that you could actually buffer that V bias, because if you kind of have a rough understanding of Ohm's law, another issue with the voltage divider that is true of all these sort of simple resistor series voltage dividers is that if at that V bias point we started adding other circuits or other things that can draw power, now that voltage there is actually going to change. So that 4.5 could turn into 4 or something, or just go to a different value that we don't want. So another more professional option is to actually buffer the voltage that we would want at the V bias, so that it can have low impedance, so that when more things add on to it, it won't fluctuate that point, which is good, and it will just be more stable. So yeah, I know I'm throwing a lot of random stuff at you, but these are kind of things that if you don't know where to start, just terms to maybe search up. You don't have to dive into this huge electrical engineering course to just make simple schematics for your guitar pedal. There's simple things like high pass filters, which do have this little equation right here, 1 divided by 2 pi, and then the resistor value in ohms, then your capacitor in farads. It's pretty simple to find. You'll see that's just done where you have a capacitor with a resistor going to ground, and you'll see this a lot maybe if you go on those websites where you study other pedals, and you could just plug those values into that equation to kind of see what frequency that cutoff filter is at. So that's really handy. Another thing with the start of the buffer circuits is you'll typically see a capacitor just at the very start of it. This is typically your AC coupling capacitor. That's because capacitors will block DC signal, so it can just help with that AC signal coming in from your guitar. It's just, there are all these little standards that you'll slowly learn, all these little building blocks. You don't have to understand like the exact atomic structure of what's happening in a capacitor to just understand how to use these little parts in your circuits. There's other really common parts, like after the DC jack, you'll commonly see a diode, which is just helping block those like reverse polarity protection. You'll typically see what are called Schottky diodes, the like 1N 58 something, I don't know, I'll put it here, but that's like a super common one you'll see. That has like littler voltage drop than some other diodes will have, so it'll just keep your signal better. And then you'll commonly see lots of capacitors coming from your power to ground. These are all just smoothing things, or things for like RF, yeah, like just radio frequency, all this stuff. But yeah, a lot of times just you could steal them and throw them on a breadboard and then learn how to put them on a PCB. But the kind of, again, the reason I didn't end up throwing all of this is, one, I'm like not a professional at this. All the other stuff I taught in this course was like super simple stuff. It's just kind of hard to piece together, so I felt confident teaching it. Whereas this stuff is a lot more complicated, and I don't have that electrical engineering background. But also, since the point of the course is to create your own unique pedal, there's a lot of PCB design concerns that come in once we're adding all of these different components that are honestly probably the trickiest part to deal with, at least for me. Like, understanding some of this buffer stuff isn't that hard, but you'll have to really Google and search for all the design considerations that you need when making PCBs. And I know for a lot of my first ones, I was pretty much just copying some schematics I found online. PCB would come and it would just be super noisy, way noisier than if I just didn't have the buffer, because I had no idea what I was doing. I was just randomly putting everything together, and I thought it like looked pretty or something. But yeah, it takes some extra steps for sure, but it would be worth it in the end. I will also just say, if you make this pedal from this course with no buffer, but you're using it on a pedal board, a lot of times you're probably fine, because a lot of pedals have output buffers that are like pretty much protecting that next stage. So as long as your pedal that you just made isn't the first in your pedal board lineup, then you're probably not really having that much tone loss at all. So it's not like a huge deal to worry about, but it is something to note. And if you ever really want to sell this stuff, then it is definitely the next step in your journey. Besides, obviously, if you are going to programming. All right, I don't even know where I was in this, because I noticed the camera just wasn't focusing at all. So if it was unfocused for a lot of that, I'm sorry. It is right now. Okay, lock onto my eyes. All right, moral of the story, V equals IR, that's your next step. Impedance, that's your next step. You got this. Simple little high pass filters, op amps, buffers. Focus. But enough of my rambling. We're done. If you've made it this far in the course and maybe have a pedal by the end of it, you have my sincere thanks. I would love to see what you build, or more than anything, I'd love to hear the music you make, because that's really all this is about. You know, I made this course not to teach crazy technical people about anything, but I think that for just like a random guitar player or a random musician or anything, that this stuff should not be gate kept, and it's actually a lot simpler than people think to just get an end result. You know, obviously all of the fields I covered here are huge. You know, you could have entire careers just studying this and stuff of each individual thing, but to just do and make cool pedals, you don't need years and years and years of experience. You just need a little course. So yeah, if you have any more questions, feel free to reach out to me at my email or just comment down below. The GitHub repo is available with all the code from this course and some extra resources. And yeah, this took a lot of time. I would appreciate a subscribe. All my videos are going to be pretty related to this, and if you have the backbone of knowing all this, then you might get more appreciation of some of the projects that I have coming. I'm going to do a lot of stuff involving the Daisy and PCBs and everything. So if you like this, then you'll enjoy in the future. I'm not going to be mainly tutorials. I'm hopefully just going to post more quick fun stuff showing projects I build, and then kind of obviously telling you how to do it. And I'll always have documentation for my little projects. So subscribe if you want more of that, hit like, all that stuff, and I will see you soon. Thank you.